Hello, my name's Roberto Lopez, and I'm the program chair of S3, Slope, Slides, and Stabilization. We would like to thank the committee chairs for the two committees that organized this event. Chris Ramsey, with the Deep Foundations for Landslides and Slope Stabilization Committee Chair, Ed Lazinski, and Jeff Seeger, co-chairs of the Anchored Earth Retention Committee. And many thanks to all the people that helped put this program together. This is the Technical Program Committee. And I take this opportunity to ask anybody interested to get involved with DFI committees or conference committees such as this one. Thank you to our sponsor, our virtual event key and online proceeding sponsor, Berkeley. Thank you to our program ad sponsors as well, ECS, Schnabel Geostructural Design and Construction, Rock Science, and PEI Rock Drills. And thank you to our cooperating organizations and media partners. So all attendees are in listen mode only. In order to make for a better experience, put the screen in full screen mode. Questions and comments can be entered at any time during the presentation. You have a question box that you can see in your screen, and you can type your question there. Please note the video and audio recording of this webinar are prohibited. PDA certificates will be emailed, and online conference proceedings will be available within the next 2 weeks after the seminar. So let me introduce our keynote lecturer, Mr. Ben Turner of Dan Brown and Associates. He will speak on incorporating deep foundations in LEM slope stability analysis.
All right. Thank you, Roberto. Thanks, everyone, for spending part of your day with us here today. We're going to start this presentation with a couple of poll questions for the audience to answer regarding the subject matter of today, using deep foundations in slope stability analysis. So this is the first question, and what's going to happen is you're going to see these questions, and then it will pop up as an actual poll, and go ahead and click on the answer. You don't have to answer each one if it doesn't apply to you or the type of work that you do. So the first question is, which slope stability analysis method do you use most frequently? So now it's going to switch to a poll, and go ahead and just select the bubble next to the one you use, and then you're done. And we'll advance it to the next question. All right. Okay, thanks. So we got close to 80% of the people selected that they use the limit equilibrium method most frequently, and then another 15% some type of continuum numerical modeling. So that's good. What I'm going to talk about today is directly applicable to the first method there, but as you'll see from our software presentations, is also broadly applicable across any analysis method. All right, we'll go to the next one here. There we go. What type of slope stability analysis do you use most commonly? 2-dimensional, 3-dimensional, or one of the other options there? All right, good. Thank you for voting quickly there. We got 95% of people said they're doing 2D. So we're still seeing a relatively small percentage of analyses done in 3D. We got one person doing 5D analyses. So we'll look forward to hearing from you on the details of that during the Q&A session. Okay, 2 more questions. Hang with us here. What methods of slope stabilization do you commonly design or construct on your projects? And I believe you can select more than one option here. So whether you're an engineer doing design or you are out building these things or involved in the field, which are you most commonly implementing? All right. So it looks like we got a fairly even split between a little bit of everything, all these technologies being implemented, and then even something else other. Okay, good. So that's informative. And then the final question is related directly to what I'm going to talk about. And the answers are a little wordy, so bear with me. When you're doing limit equilibrium method analysis, which most of you indicated is what you're commonly doing, how do you represent deep foundation resistance in the model? So you can go ahead and read through each of those and select the one that's most appropriate or choose other. Okay, that's probably good, Marianne. All right, so slightly more than half of you indicated that you are assigning the shear strength of the structural material, be it concrete or steel, etc., directly to some slice in the model or some geometric zone. And then I guess you could select more than one option here. So about half of you are saying you manually input it from a separate laterally loaded pile analysis. Some of you are relying on the structural engineer to give you guidance here, and then close to 40% are using some software that has capability to do the slope stability analysis and a pile analysis simultaneously. Okay, good. So that was the last poll question, and I think seeing that information will be informative for our software vendors and for all of us on the organizing committee. So thank you for that input. My presentation is called Incorporating Deep Foundations in Limit Equilibrium Slope Stability Analysis, AKA do not apply pile shear strength to material zones. So that's a little bit tongue in cheek, but that's directly related to the last poll question there. What I hope to highlight and impress upon you today is that that can often be an erroneous method of approaching a slope stability analysis that includes deep foundations, because it doesn't address the true mechanism that might develop. So I'm going to explain today how to identify that mechanism and then correctly implement the force. And then that's what our software vendors are going to explain how to do and how they did for our example problem with their respective software packages. So my presentation is basically broken down into two parts. I'm going to talk about the fundamental mechanics of the deep foundation resisting elements, which I just refer to generically as piles. It could be a driven pile or a drilled shaft or some other type of novel deep foundation element. And then I will explain the problem statement that was given to the software vendors and kind of the baseline information so that each of them doesn't have to spend too much time going through it. So let's dive right down into the mechanics here. On the left is a crude illustration of a free body diagram for the method of slices or limit equilibrium slope stability analysis. So the peach colored shape there represents the potential slide mass, and it has a body force, so its own self weight acting vertically due to gravity. We can resolve that force into components that are normal and parallel to the potential slip surface. And then we're also evaluating the shear strength of the geomaterial, soil or rock, along that potential slip surface. And once we've worked out what all these forces are, we can solve for force and or moment equilibrium to evaluate whether or not the slope is stable. So that in a nutshell is limit equilibrium method of slope stability analysis. When we add a pile into the mix, you can see things get a little more complicated. So within the depth range of the soil or the ground that's moving, there's load transferred from the ground into the pile. And so that's represented by this red kind of pressure distribution on the upslope side of the pile. Then where the pile is embedded in the ground below the slide plane, it transfers load back into the ground. So the ground is now providing resistance. So there's a load path from the ground, from the slide mass into the pile, and then into the ground below the slide mass. So if we now represent that or add it to our free body diagram, it's been sketched in on the right with that green line representing our pile. And if we're looking at a true free body diagram where forces act on the external boundary of the free body, we can represent the pile by the resultant shear force that's mobilized at the slide plane depth. So that's what's shown with that green arrow and the V. Strictly speaking, the location of that force would actually not be on the boundary. It would be up a little bit because it should be the resultant of the pressure distribution in the slide mass. So for example, if it's a triangle like this, it would be about 1/3 up from the base. But for simplicity, it's sketched right there. Okay. Oop, I think I skipped one. I also want to point out that I'm only showing shear, and I'll talk about the mobilized shear force during this presentation. But what's not shown, and what you know from analyzing piles, is that if you make a cut, there's also an axial force in the pile at that depth if there's a component of vertical ground motion, and there's a moment. And those, the same things that I'm going to say apply to those forces, which can absolutely and should be included in the slope stability analysis when computing force or moment equilibrium. But we're going to focus on the shear force here today. So that's the shear force by inspection that acts on the free body diagram. So the question is, what is the value of that shear force, the appropriate value to lose in a slope stability analysis? Well, when you're doing limit equilibrium slope stability analysis, by definition, all components of the system are at a limit state. That's what the limit means in limit equilibrium, which simply means that they have provided or mobilized their full available strength. So for the ground, for example, it's at its shear strength. We don't directly consider the amount of strain that it takes to get to that point. We just assign the shear strength as a stress or a force. Likewise, when you incorporate a pile into a limit equilibrium slope stability analysis, my opinion is that the resisting force should be representative of a pile soil interaction limit state. Now, there's a few caveats there. Related to how we combine a factor of safety with the slope stability analysis and apply that also to the pile resistance. So when the pile's at a limit state, you could choose to apply a resistance factor or a factor of safety, depending on what design framework you're working in, allowable stress design or LRFD, to that resisting force before you bring it into the slope stability analysis, or you could allow the slope stability program to apply the same factor of safety that it applies to the geomaterials to the pile. that choice is yours as a designer. It can be handled either way. You just need to be aware of what you're doing. But what I'm speaking about today in my kind of fundamental presentation here is going to take the factor safety part out of the discussion. And we're going to focus just on identifying the limit states, which you need to do even before you apply a resistance factor or factor safety to that. So there are multiple limit states that are possible. I've identified 4 that we're going to look through in detail now. And your job is to identify which one controls, which means it occurs first or at the smallest amount of ground displacement. And then that amount of resistance represented by that limit state is what you should implement in the slope stability analysis. So the 4 limit states that I've identified today are 2 geotechnical limit states and 2 structural limit states. The geotechnical limit states are so-called flow around failure, when the landslide mass undergoes a large displacement around the pile, or the pile itself could undergo a geotechnical failure below the slide plane, basically just tipping over. And then the pile could fail either in shear or in bending or flexure structurally. So your job as the slope stability analyst or engineer doing this analysis is to figure out which limit state controls in order to define the appropriate force to implement back in the slope stability analysis. Okay, so let's look at each one of these in a little more detail and determine how you would identify whether a particular one is the controlling mechanism. The first is the so-called flow around failure. So there's a maximum amount of load or stress that the moving ground can transfer into the pile before essentially a passive wedge or mechanism develops, and there's not going to be any more load transfer, and the soil's just going to flow around, as the name implies. The way you can identify this is by producing a chart that's similar to the one shown on the bottom of the slide here, which I always encourage you to do when you're doing this type of analysis. So this is simply plotting the shear force in the pile at the depth of sliding, the mobilized shear force, as a function of how much the ground has displaced relative to the pile, basically the landslide movement or the slope movement. What you see in that plot is that it reaches an asymptote around about, say, 35 kips, where increasing slope displacement no longer increases the amount of mobilized shear force. And that's simply because this flow around mechanism has occurred. The ground is going to continue to move and will not transfer any more load into the ground, as long as one of these other mechanisms hasn't already occurred and is causing this behavior. So just because you see this plot that looks like this, you're not automatically done. You need to make sure that the other mechanisms haven't occurred, particularly that a structural mechanism isn't giving you this behavior. This is likely to control if the slide mass soil is weak or relatively shallow, and we'll look at that again in a little more detail. The second failure, geotechnical failure, is a pushover. So this is, as the name implies, kind of self-explanatory. The load on top above the slide plane is too great for the amount of resistance available below the slide plane, so the whole system simply pushes over, and of course that's going to lead to large ground displacement. And then either a shear or flexural failure are possible in the pile. These would typically occur either immediately below the slide plane, or if the pile is socketed into a stiffer material or rock at some distance below that, that could be the location of the maximum moment or shear where a structural failure would occur first. Okay, so the motivation for this presentation is that a method that is commonly employed, that I've seen over and over again, and I'm sure a lot of us have, is that oftentimes people jump straight to assigning the structural shear strength of the pile element as the resisting force. So for example, say we're talking about a reinforced concrete drilled shaft. You could take the shear strength of the concrete, multiply it by the cross-sectional area of the shaft, and say that that's its shear resistance, maybe adding in some shear strength of the reinforcement as well. Or if it's steel, you take the cross-sectional area of something like a steel pipe or an H-pile, multiply it by its shear strength, that gives you a force. Okay, if you implement that in the slope stability analysis, you are implying that that's the mechanism that develops first before any of these others do. And as you'll see here in the next slides and in our software example, that's unlikely to be true for the vast majority of cases. And so it would be incorrect to do that, and potentially that's a that's a drastic overestimate of the amount of available resistance. So you would be overestimating the factor of safety or stability of your slope if you did this, if you use this method. So let's dig a little deeper and kind of question, is it possible to get a pile shear failure before one of these other mechanisms develops for typical conditions? If we have a shallow depth of sliding, particularly if it's in soil, the maximum load imparted from the moving ground against the pile is unlikely to be enough to shear through the pile, basically. So I've shown here two plots with two examples from real projects where we were using relatively small diameter deep foundation elements, and that's on purpose for the purpose of this example because they have low shear strength since they're relatively small cross sections. This is with an 8-foot deep layer of sand on a 20-degree slope, sliding along a weak clay layer. So I'm plotting the same information that I already described before. It's the mobilized shear force versus the amount of slide displacement. And you see that for a HP 14 by 89 driven steel pile or a 16-inch diameter reinforced concrete pile, in this case it was installed as an auger cast pile, the maximum soil pressure that can be exerted against the pile is not enough to mobilize the full shear strength, particularly for the steel. It's not even close. So that's a shallow slide. For a deep slide, you're more likely to get a flexural failure before you get a shear failure. And the reason for that is pretty simple to understand if you think about our free body diagram and the mechanics. As the slide plane gets deeper, the shear force, which is basically just equal to the resultant of the pressure distribution acting above the slide plane, is increasing essentially linearly with depth. More soil pushing against the pile just makes that much more force and shear force going into it. But the moment demand right below the slide plane is going up exponentially. And that's because it's the product of the linearly increasing pressure distribution as the slide plane gets deeper, times the moment arm, which is also getting deeper, acting at the location of the resultant. So that's going up exponentially, which means that the deeper the slide plane gets, our moment is basically going off the charts while the shear just kind of tracks up linearly. And as a result, you're most likely going to reach the nominal moment strength of your section before the shear strength. So what's shown here is a different project where we were looking at the ability of a group of driven HP 14 by 117 piles supporting an abutment pile cap to also resist the potential slope instability. And even with a relatively large amount of ground displacement, it's on the order of 12 inches, we reached a flexural failure. You can see the curvature plot has that spike because it's formed a plastic hinge, when in this case, the shear demand to capacity ratio is only 10%. So if you just input the shear strength of this pile into your slope stability analysis, you would be overestimating the amount of available resistance that it could provide by a factor of 10. So it's not a trivial difference. That would be a big difference in your slope stability calcs. Okay, so here's what I would propose is an appropriate method for determining the amount of resistance to incorporate back in your slope stability analysis. The bottom line is you have to do one way or another a laterally loaded pile analysis. So one way to do that, if you use a limited equilibrium slope stability program that doesn't have that functionality or capability built in, is to do a separate laterally loaded pile analysis, for example, using LPile or any equivalent software, where you make a model that matches the ground conditions. You've identified a depth of sliding from your slope stability analysis that you want to evaluate, and you set up a model basically like that, and you'll see that in our software vendor examples. And you displace the ground relative to the pile, and you track the mobilized shear resistance, but you're also looking to identify which mechanism is realized first. So these next series of slides basically just detail the same thing I've already explained. You'll have these slides as a reference for how to go through this process in a little more detail. Essentially, you're just going to track if each one of these mechanisms develops. Do you have a flow around failure? Do you have a pushover failure as exhibited here by this rigid body rotation that goes to a large displacement? In that case, just note, make the pile longer. If this is occurring, you shouldn't let it. You should just make the pile longer. So that's an easy fix. Or are you getting a structural failure, which of course requires you to have knowledge of the nominal moment and shear strengths of the section. So there's no way to do this without doing the laterally loaded pile analysis and also having an actual trial pile design in mind from which you can calculate its structural strength. There's no way to do it otherwise. So if you're thinking you can do this purely in the geotech world as in the slope stability software, unfortunately you can't. You need to work collaboratively with a structural designer or have that capability yourself. Okay, just to really point out a few more things that would be incorrect ways of doing this. If you draw zones in your model in the geometry that represent the pile, and you assign to that slice the structural shear strength of the pile material, like for example, if it's concrete and you make a Moore Coulomb model where the cohesion is set to 5,000 PSI because that's the strength of your concrete, you are not doing this correctly, because limited equilibrium slope stability software is not set up to do a lateral pile soil interaction analysis. So you might think you're doing it right, but basically you're skipping that part of the analysis and could be off by a big margin. I'll say that a lot of slope stability software, essentially all of it, in my experience, all the different programs that are available, give you a way to directly input the structural shear strength of a pile. And so in that regard, I won't say they're misleading, because all programs require the user to understand what they're doing, but they sure make it easy to do this, in what I'm describing as the wrong way, to just input the shear strength of the material. So be wary of that, and be aware that you need to perform a separate analysis to determine what that force is. Even though I've been talking about limited equilibrium analysis, you don't get off easy just because you go to a continuum numerical modeling approach. The same thing applies. You can't simply define zones of geometry and then assign, a constitutive model that represents concrete or steel, for example, to those zones and think that you're done. You have to take care to set up your numerical model in a way that actually represents the pile soil interaction. Typically, that's going to mean you need to implement structural beam column elements to represent a pile, and also define the interface between the pile and the ground to make sure that you're capturing that interaction behavior. So you don't get off easy by just going to that type of analysis. Okay, some final thoughts to wrap up the kind of mechanics part of this presentation. The bottom line is that shear failure is unlikely to occur prior to a flow around or a flexural failure in most of the scenarios that I've looked at. It is possible to get a shear failure in a pile, particularly if you're going through a rock and the slide plane is between boundaries of rock, like on a bedding plane of a sedimentary deposit. You can shear through a pile before failing it in flexure. But for the vast majority of cases, it's usually wrong and therefore, quote, unconservative to apply the pile shear strength to material zones in slope stability analysis. I'll say that the good news is you have control over which mechanism occurs first. As the designer, you can adjust the pile layout, the spacing, the diameter, etc., if you're getting a failure mechanism that isn't the one you want. And to that end, I would advise you that if you're coming up with a case where shear failure is actually occurring first, you probably want to adjust the layout, because shear failure tends to be brittle. This is why in structural design, we intentionally design for flexural failure to occur first, because it's ductile, meaning it displays some amount of displacement before the failure actually occurs. And certainly that is a good thing when we're talking about stabilizing landslides. We don't want a brittle, all of a sudden landslide failure. We'd rather have it moving a little bit so that we know we have a problem and can do something about it or evacuate before something goes bad. And then just sort of a philosophical point on design: an efficient design balances multiple limit states and doesn't let one govern over the other by a large margin. Okay, so I'll briefly now describe our software problem that's been provided to the vendors. So it's based on a real landslide, which is called the Trunk Highway 2 landslide in Crookston, Minnesota. The most recent episode of landsliding occurred here in 2003, but there was a prior landslide in 1933. So the slope is shown in Google Earth on the lower left image there, outlined in yellow. You can see it's on the bend of the Red Lake River. And that picture is a little deceiving because I believe that's after the repairs were implemented. you don't see all the damaged structures that were destroyed and condemned and removed, like that house on the lower right. You can see that the damage was pretty severe and makes for good photos. The fix that was actually implemented was these so-called shear walls constructed as slurry walls parallel to the direction of sliding. You can see them there in the plan view, and you can see in the center photo a photo during construction. All the information that we got for this problem came from a report written by Barr Engineering for the Minnesota Department of Transportation. We chose this project for the software example because the ground conditions and the geometry are really well characterized. As you'll see, the stabilization that we asked the vendors to analyze uses drilled shafts. It doesn't look at what they actually did, which is the slurry walls. And that's not at all meant to be a condemnation of the stabilization method that they chose, which it's my understanding worked very well. Not at all. We simply used this problem because the geometry and soil properties were very well characterized, as I said, by extensive in situ and laboratory testing. And that gave us a great problem to work with and try any stabilization method we wanted. Also, because drilled shafts were not the actual chosen stabilization method here, we didn't want the software vendors to feel like they were being compared to the quote real stabilization that was implemented. We wanted them to have full creative license to vary the design and come up with what they thought was most efficient. So the geometry of the problem is based on this cross section A. I know you can't read that text probably, but it points out that the ground is very well characterized by in situ testing, cones, borings, piezometers, inclinometers, and you see these terraces on the ground surface, which are actually the scarps of the previous episodes of landsliding. So I did an analysis to define the baseline conditions and establish that the site is quasi-stable. The factor of safety is about 1, given these material properties shown here. So the bad actor, the one to look at, is that green layer, which is a soft clay, the Whop formation clay, and has a long-term drain friction angle of only about 15 degrees. For the problem at hand, we didn't include any changes to the ground surface elevation or changes in water levels, so it's that long-term drain property that applies. It's also worth pointing out that we provided a simple hydrostatic groundwater surface, even though in the real landslide and as detailed in the Barr report, artesian groundwater conditions and a rapid drawdown of the river level are actually what was attributed to the landslide. But we just wanted to simplify that because we're not diving down into the details of water and slopes. We're talking about the implementation of deep foundation elements. So as shown here, this is what we provided for the stabilization alternative to be addressed or investigated. It's 3 rows of 8-foot diameter drilled shafts. They're spaced 40 feet in the plane of the slope and then 24 feet at a plane, so 3 diameters. And they're socketed 2 diameters or 16 feet into this very dense refusal blow count till layer that's shown in orange. We gave nominal structural material properties, including a concrete strength of 5 KSI, a transverse reinforcing detail, and then the longitudinal reinforcing detail, which gives you a reinforcement ratio of about 1.5%. And here are the prompts that the software providers were asked to respond to in their presentation. The first one is just to identify what factor safety did you compute for the existing conditions. And this is just to make sure we're all at the same starting point. The second one is we wanted them to identify what failure mode is controlling the resistance provided by the drilled shafts. That is shear, flexure, or geotechnical stability. So this is the same thing I was just talking about. We want them to identify what controls and then tell us as users or potential users of the software how they made that determination. So that was part 2A, and then the remaining ones are more nuanced and relate to kind of the subjects they'll go into detail about. So what is the computed stabilized factor of safety with the drilled shafts as specified? What are the demands on the drilled shafts that should be used for structural design of the shafts, shear, moment, and axial demands? Part D, what amount of slope displacement is anticipated for the safety factor computed for part B? So if you're telling me the safety factor is 1.4, what displacement goes along with that? And what is the meaning of that displacement? And then the last part, what amount of slope displacement is actually anticipated? If I go out there and build these drilled shafts like I just showed, how much is the ground actually expected to move? And then I weighed in here kind of with my own opinion. For example, in the context of a limit equilibrium analysis, this might be associated with a factor safety of 1.0 or referred to in the context of, quote, service level displacements. So you'll hear more discussion of that from the providers. All right, I'm gonna wrap up with that, and this is just another reminder in case you didn't catch Roberto saying it in the beginning, that you can type your questions into the box on the right in the dashboard whenever you have them, and the moderators working behind the scenes will assign those questions to the appropriate person, and we'll answer all of them during the Q&A session at the end. So with that, I'm going to, we're gonna begin now the software vendor panel part of our event today. And I'm going to introduce our first presenter, which is Augusto Lucarelli from Itasca Consulting Group. Good morning, Augusto, or afternoon, evening.
Good morning, everyone. Good afternoon for me. I'm across the pond now, so hopefully the connection is working fine and you can hear me well. Do I have control? Okay. Perfect. It happens that I was involved in the design of the real slope, so I felt particularly interested in try to revisit the analysis that were done a few years ago to see what we can be, if other alternatives. Obviously, other alternatives would work too, but the main focus of this analysis is, just like Ben said, to try to understand really the mechanics of how deep foundation are working. So we didn't focus on too complicated geometry. We just took the cross-section AA that Ben was showing and extruded the so-called 2.5D models, so 24 feet out of plane, and put piles in the middle. As far as the pile are concerned, I modeled using the 1D embedded pile elements, which is the typical type of approach in this type of analysis, but also consider that 8 feet diameter is a big shaft. I was curious to see what is the effect of accommodating the real geometry of the pile in the model instead of having a volumeless beam. And we'll see that this also has an impact, especially at large deformation. The soil is the same parameter that Ben was showing, water table the same. The approach in terms of analysis is based on the strength reduction method. I'm just going to touch later on. And in terms of support alternative, I think I probably I went a little bit too far, but I was curious to see how different alternative in terms of other structural approaches like micropiles or anchors or a combination of this mix could help to provide a better performance and a better safety factor. So at the end, the focus of this presentation is performance comparison and understand the failure mechanism for different type of support. The presentation organizes two sections. You will see that there is a lot of words. It's supposed to be a handout. I'm not reading everything, so I'm just gonna skip through the main important slide, and then you can go and read on yourself and come back with questions even after the webinar. Okay, so just mention about Flash3D. Of course, I use Flash3D to run this analysis. Is a software package that has been around for over 30 years, is worldwide used, and you can get more information. I'm not going to spend much time on this. If you go into our website and have a look and maybe download the demo and look at the capability. Let's talk instead about the strength reduction analysis. Like many other software, Flash3D comes with a routine to run a strength reduction analysis method. We have to, I think that everybody is aware that the strength reduction analysis, especially when there are structural elements, allows for not pushing in place the reaction of the support, and so it provides a better, in my mind at least, understanding of the mechanism, including the potential evaluation of multiple mechanisms that are forming a different level of strain, and therefore the support would be mobilized differently. The cons, obviously, is that it usually takes a little bit longer to run. It could be from minutes to hours, depending on the complexity. But you know, for a significant, important project, it's still not prohibitive. Oops. Sorry, I'm having trouble here now. Okay, so in terms of mesh generation, again, Flat3D comes with an extruder. It's very simple. You just import a background image here, and you decide what mesh density you want, and in less than a minute, you have the mesh. There are other options, but I'm not going to talk about other options for more complex geometry right now. In terms of structural elements, we have several possibilities in terms of 1D beam, cables, and piles, and then 2D shell, geogrid, and liner, and a bunch of other utilities like links, for example, that allows to connect the structures together. And on the right side, just a few examples of the complexity of geometry that you can create. Okay, this is enough. We already shown this section. Let's get started with the analysis. This is just a summary of what Ben has already shown. Okay, material. Oh. Sorry. Material property and geometry. One decision that we have to make, especially in this circumstance, is we have to start imposing a stress, and we have to do a back analysis to bring the slope into a failure condition. So we have to decide if we are basing our analysis on the post-failure geometry or pre-failure geometry. I decided to just concentrate on the post-failure geometry. It provides us a little bit different shear failure location, especially here close to the highway. But for the purpose of this exercise, I decided to skip with this one, to stay with this one. So in terms of constitutive model, I use more Coulomb for the clay and the upper sand, and plastic hardening for the art till. This is the water table location, and this arrow here that you see is just the total pressure applied at the bottom of the river. Okay, so in every numerical model, we have to initialize the stress, and we have to initialize the stress in such a way that the model can reach equilibrium. So in this case, for example, I applied an undrained shear strength of 0.25 sigma prime V with a minimum of 15 kilopascal. Otherwise, we would have seen a local mechanism here that is meaningless. And then after we have the model in equilibrium, we need to start reducing the strength in such a way that replicate similarly the mechanism that we have seen on site. So one way to do it that I find convenient is just to plot the strength reduction factor against some sort of the measurement of displacement. It could be displacement, it could be strain, it could be moment, and so on and so forth. And we see that we observe failure once we observe the displacement that it's kind of going up exponentially. It means that the model does not converge anymore. And in this case, we have a strength reduction factor around 1.12, which correspond to 0.22. Okay, now we have brought the model into a metastable condition, which represents the situation that we have before installing any type of support. Now we are ready to install the support. And this is the first solution, the basic solution that Ben described. So we have the 3 drill shaft on the left. We have the alternative with embedded pile, and on the right, the alternative with 3D solid piles. And I also included all the reinforcement inside the steel cages in terms of longitudinal bars and also the spirals. Now, what do we get? Oh, this is just a cross-section representation of the structural layout with the constitutive model for the material in terms of concrete and steel. I'm not going to talk about in detail of this. And what the sectional analysis gives us are usually 3 aspects. One is the truss bending diagram. Second is the moment curvature, and third is the axial shear diagram. All of this nonlinear behavior has been implemented inside Flat3D. So while the strength reduction process goes, we know when we reach cracking in the pile, we know when we get into ultimate failure, and we know if we have shear failure or bending moment, and we also know what type of geotechnical failure, if any, would develop during the process. So essentially, we have the full picture combined together in the model. Okay, this is a typical result, for example, for the situation with embedded piles. So these are 1D volumeless pile, And again, you see on the horizontal axis the strength reduction, and the vertical axis the displacement. I've divided the slope into portion, an uphill portion here that is represented by the blue line, and the red line is representing the downhill portion. So the first thing that we see in this slide is that there are multiple mechanisms that are forming. We have a lower mechanism, and we can decide temporarily to ignore that. And also we have a upper mechanism here, and once these mechanisms are exhausted, then we mobilize the full slide like on the right side here. So for example, if we take a reference number like safety factor 1.3, we would see a displacement of the upper volume, which is the one that is most interesting because we have the highway here, that is in the order of, let's say, 400 millimeters. It's probably too much, probably not acceptable. Although the structural capacity in terms of bending, we are at 70% of capacity and even lower in terms of shear. Now, if we keep reducing, obviously, we see that the curve is already in a very steep shape, so the displacement keeps growing very fast. And we reach quickly the structural capacity. In other words, what we are saying is that this solution is probably too deformable because essentially it is a cantilever pile, and it needs a lot of information to mobilize the structural strength. Now, this chart shows what type of mechanism is mobilized first. The red line is the bending moment utilization factor, and in blue we have the shear utilization factor for different safety factor as a reference. We see that the red line, even for this small embedment, which is just 2 diameter, the bending moment is dominating the behavior until we get plastic hinge formation up here, and then the shear obviously catches up, and we get a complete structural failure. But the displacement is already so high that is probably meaningless. So I would say that in this case, the dominant failure mechanism is loss of performance, so excessive displacement, or let's call it geotechnical failure to occur. Now let's see what happened when we switch toward a full 3D representation of the piles. Now the situation is a little bit better in terms of displacement. Obviously, the geometry of the full 3D pile is capable of capturing a better interaction, although we still see the fundamental presence of a lower wedge forming here and also a potential upper wedge forming here. We get less displacement because there are other mechanisms that the embedded pile cannot capture. But again, at safety factor 1.5, we have the full structural mobilization in terms of steel capacity and also concrete capacity. You can read in more detail below that. The slide. Okay, this is showing the mechanism for the pile in this case. Essentially, in this case, it is controlled by concrete failure. The concrete would crash in compression. This is a heavily reinforced section, and we see also the buckling here locally of the pile, of the longitudinal bars, and finally the plastic hinge form with yielding of the steel. Next one should be a short video. Hopefully I can get it started. That would show how the mechanism would develop. If you follow the blue and the red line, that shows the mobilization of the displacement for the slope. And you see that the lower part is gone at around 1.3 something, and the blue line keeps going because that is the portion of the slope that is pushing against the pile, and you see that how this pile are displacing until we get the structural failure. Note that below 1.5 we have a displacement that are higher if you look at the red portion of the picture. Okay, so this concludes the basic solution. I'm just highlighting on this slide the mechanism that we are losing when we use drill shafts for this type of analysis. Essentially, we are losing the base component and also the shaft interaction due to the rotation of the system. These are becoming important at larger deformation, as we will see later. Next one is, okay, let's see what happens if we embed, instead of 2 diameter, 4 diameter, the piles. We get a little bit better performance, but not really much. We still are not able to get to 1.5, and the displacement is still significant. So this is certainly a solution, but it's still based on a cantilever system. Again, now we are embedding more, and so obviously what I would expect is to have even a more pronounced gap between the bending mobilization and the shear mobilization. This is actually what happened. If you remember, the 2 diameter embedding, the red and the blue line were kind of traveling together, while the longer the embedment, the higher the bending mobilization is. What would happen instead if we change the static configuration, like for example, adding a top beam? So instead of relying on a cantilever cross section only here, we would change and transform the support into a frame. This is highly beneficial. We are reducing the displacement significantly. We are also changing where the bending moment and the maximum bending capacity or demand is localized. Now is at the top, close to the beam, can access much way more easily than having a plastic hinge down at the bottom, and we can go up to 1.5 with a displacement that is still probably acceptable for a state limit. Obviously, it doesn't solve this situation. You know, this is a point that I want to make. Sometime I've seen, okay, I don't care about this mechanism. I'm going to ignore it, and I'm just going to put a high cohesion or something like that. In reality, it is like putting ground improvement. And we will see that taking care of this wedge in the other solution is actually improving the performance of the slope as well. So everything is kind of cooperating together. Multiple mechanism and structural organization must be analyzed together. This is just the curve of the displacement and the form shape at failure. The failure is in bending again, and it is located at the top connection with the beam. Okay, now let's switch. I can skip this one, I already mentioned. Now let's change completely type of approach. Now we have, sometimes it's difficult to organize the shaft, and we need to provide a solution with small diameter elements like micropile and anchor. So I set up a system that is only based on micropiles, organized in an A-frame shape, and also try to solve the bottom or the lower mechanism here. Now we see that the red and the blue line are moving in parallel, and we have a more global mechanism that will form, again, triggering bending failure in the micropile, but much later, because this system relying on axial force, Stratton tie system, and so is much stiffer than a system that relies on bending. It's not possible always to do this type of approach. Here in this situation, bonding, the bond and the ground bond becomes a significant issue. So also the control and execution becomes important. But just to show the difference in terms of performance that you can get switching from drill shaft, in this case, cantilever, to adding a top beam, or to switching completely toward axial control type of mechanism. We can go above to 1.6 or even higher. Finally, and I'm almost done. Of course, the mechanism here in terms of structural is controlled by bending. Micropile will break in bending. The shear here is the green line, is not even registered almost. Just for your information, these are the property of the micropile that I've used. I don't need to get into this detail. We can quickly move forward. This is a combination of different systems. So I kept the drill shaft here, and also put micropile here as support and anchors in the situation. So this is a mix of different type of approach. Try to block the head of the drill shaft instead of leaving cantilever, having a system that can control the horizontal deformation. And this is actually works pretty good and seems to be the best one, and would allow also to optimize the diameter of the drill shaft. I didn't do that because of the time, but in theory, this solution would allow for reducing the diameter and the reinforcement of the drill shaft. We see that that we can easily go in this with this one to have a safety factor 1.8, and still the performance is very desirable, because we are talking about a few inches of displacement. Finally, since I did also the analysis for the shear wall, I was curious to see where is the shear wall solution in this situation. Consider that this approach is based on Andrean shear strength, and for the design, didn't use the shear strength, the Andrean shear strength, but an effective stress approach that I will talk and mention a little bit later. We see that, as Ben was mentioning, shear mechanism is brittle. We see that we get a better performance before we get to failure, but once it fails, it goes pretty fast. Finally, I guess it's important to summarize in such a way, this is a kind of a busy chart, but bear with me for a second, is the summary of all the solutions that have been analyzed in a single chart. And it's kind of a very easy to track what we want to get and what is the best solution that we can implement, considering the safety factor, which is only a number and usually doesn't really represent the whole system if we don't associate a level of displacement to it, a level of performance. A safety factor means that we know only the final point, but we don't know how to get from point A to point B and what happened to our support system along the path. So, for example, if we fix at 300 millimeter, a foot of displacement as a maximum displacement that we can tolerate, and we wanted to have a safety factor 1.5, we see that none of the solution based on piles and even the shear wall with this situation would satisfy this requirement. We need to put at least a capping beam at the top or a switch system and try to control the head displacement. Even a closer view close to the origin, if we want to go into a service limit state, we see that all the piles, including the 2D analysis, are kind of moving in parallel at relatively low displacement. And we see that the shear wall is stiffer, obviously, in this situation, but the solution with axial mechanism are performing better than the other one. I guess there are a bunch of conclusion and recommendation here. I'm sort of mention more or less what are the main aspects that we need to consider in a slope stability analysis, which are essentially accommodate also on measure of performance. Just don't rely on a single number that is the safety factor, which if we don't know what is the level of displacement and what mechanism is necessary to get there, it does provide only a partial information. You can read this on your own, I guess. I'm not going to spend much time on this. I want to mention just a reminder. I've seen in multiple cases the utilization of embedded pile with PY method. That's perfectly fine, but be aware that the PY method has been developed in a different context. Here is the soil that is moving, is dragging the pile. It's not like in a bridge where you have a top load and you have a reaction from the soil. So at least for me, it's very difficult to assess what is the mechanism or what is the cinematic of the system. And that is tied into the reaction that we're bringing back to the slope stability analysis program. And so there is also a factor that limits, as Lower and Braun demonstrated, that the pressure that you can estimate from an L-pile analysis can be as low as 20% or 25% of the traditional PY formulation. Okay, having said that, now I want to discuss a little bit of the limitation of the general approach. I'm struggling to understand, or let's say, the physics of reducing the strength below, let's say, a value that is minimum, like the normal consolidation value or the residual strength. And that ties into the consideration that there must be a limit in terms of strength reduction below which it doesn't make any sense to keep reducing the strength. So here in this situation, we were in a situation already in normal condition. How can the strength be lower, much lower than that? It could be, instead of 0.22, could be 0.20, 0.18, and that's fine, but certainly cannot go down to 0.10. So all approach probably need to be rethought and reconsidered, and try to, and this is why also because I tend to use effective stress approach, because I think is more appropriate for this type of a slow movement and type of stability analysis. So effective stress approach. In this case, we had good data also for from a triaxial test. You see this graph on the right. This is the red dots are illustrating the peak strength, and the blue dot are the residual strength. So without doing any fancy math, I draw a gray line, which for me represents the peak condition or a disturbed shear strength, and a very conservative assumption for the minimum residual strength that I want the, I assume that as a design shear strength. Now, the problem is that we have already mobilized the residual strength or close to it in a few regions. We have two slides, two pre-existing slides. So one approach is to start reducing the strength into the mobilize the existing slip surface, and then install the support, whatever the support will be, and then keep reducing the strength all the way down to residual. Once we are at the residual, stop. Finish. There is no other strength reduction. There could be some other cases that we want to analyze, like what would happen if we increase the water pressure, what would happen if we include creeps or other phenomenon. But in terms of shear strength, we have reached the geotechnical limit capacity in terms of shear strength. And this is exactly what I did. Start with a model that is initially in equilibrium, reduce the strength only on the existing slip surface, and guess what? The failure happens for a shear envelope that is very close to the residual. And by the way, 0.28, 0.25 is pretty much the same number. So we have these two sliding slip surface that are residual, and you see also here this jump in the displacement because this represents failure. At this point, we install the support, and we keep reducing the analysis. We keep reducing the strength everywhere now, all the way down to residual in the slip surface and also in the youth formation and in the top sand. And here's what we get. So the global strength reduction, we can travel all the way to residual. And we have a mobilization of 0.44, which means close to 0.5, which means, in my opinion, that we have already applied a safety factor of 2 for the geotechnical side, and we have a safety factor of 2 also on the structural side in terms of bending moment. And we already know that the shear doesn't come before the bending in this configuration. So what I'm trying to say with this approach is that sometimes just relying on drain shear strength and keep reducing the strength to value that are not physically possible can produce unrealistic design. And I did the same exercise, or let's say two-way conservative design. I did the same analysis with the shear walls, getting very similar results. And what I'm showing here is the formation of the tension and shear bands, mostly shear here and tension on this side. But again, we have a safety factor of 2 in comparison to the residual strength. I guess I'm approaching the end. This is the method that I tend to use all the time when I have a pre-existing slide. Trigger the residual strength or close to it. If you don't have data, you have Professor Stark's correlations that can provide you some initial information to determine the A and B parameters for fully softened and residual strength. Then install the support and then reduce the strength. Once you are at the lower limit, you can still play with other problems like water table or creep or any other type of phenomenon that you think may happen in order to evaluate the performance of your system. And that's the end. Thank you for your attention.
All right. Thank you, Augusto. Lots of detail in there. So just a reminder that the slides will be provided as a PDF, and certainly the presentation we just saw will be a valuable resource to revisit. Lots of extra commentary and discussion on the details there from Augusto was included on the slides. I think also he made some sage points about the relationship between factor safety and displacement or performance, and that it can be misleading to just think about slope performance in terms of a factor of safety, which is, after all, a number that kind of represents a condition that is just theoretical and doesn't actually occur. Okay, our next presentation is from Dr. Gary Gregory, and we'll see a different approach of looking at this same problem. Professor, go ahead.
Well, thanks everyone for joining us today. My presentation is based on a combination of limit equilibrium and PY analysis using my slope stability program GeoSpace and INSOFT's lateral pile analysis program LPILE. And this is a very simple and rational approach that is well within the capability of most geotechnical offices that have experienced geotechnical engineers, and it's worked well for me over the years. So I'll provide this approach. Also, I have a technical memorandum that covers more details that I will be glad to provide to you, and perhaps it would be included with the PDF later. All right, the limit equilibrium analysis, I'll just give you an outline of how I approached it. First of all, I analyzed a single slip surface with a non-reinforced initial condition, the same as being presented to us, because it's really important when you start to analyze a slope that has failed is to make sure that the geometry and all of the strength details and so forth are the same. So we're analyzing the same problem. And so we should, using similar methods in limit equilibrium, we should get the same factor of safety or very close. Following the single surface analysis, then I also ran a circular search for the same non-reinforced condition to see if in the search I would get a similar factor of safety. And then as a third step, I performed a highly refined non-circular search, which is called a ZRS auto search in GeoSpace. And also this was for the non-reinforced initial condition. Also, I was using the undrained strength ratio for the Huat formation, which we'll just call the soft clay, for all three of the analyses 1 through 3. And then I performed a ZRS auto search for the non-reinforced initial condition starting from a circle, but this time using a curve strength envelope to represent the the residual condition for the soft clay. And this was also applied in my steps 4 through 6, all of the steps. So then I performed the ZRS auto search reinforced with the 8-foot diameter drill shafts, which we'll call piers, at the out of plane spacing of 24 feet. And most of the time when we approach one of these types of conditions, I found that working with the design team, or perhaps in some cases it's mandated by regulatory agencies, we'll have a target minimum factor of safety in the limit equilibrium analysis, and we'll come up with a pier capacity that will achieve that, which in this case, as you'll see, is about 336,000 pound force per pier. And then as a final step, I performed the ZRS auto search again, same as in step 5, but with a simplified 3D analysis that's available in GeoSpace, and I'll discuss that more as we move on through. So in the initial condition with a non-reinforced baseline specified circular surface, I got factor safety equal to 0.995, which is exactly the same as what Ben established in the baseline slip surface. I will say at this point, I think Mike Duncan has a very good saying that your credibility is inversely proportional to the number of decimal places in your factor of safety calculation. So these values are represented to 3 decimal places only for the purpose of comparing among the various analyses, and they do not imply that it's accurate to 3 decimal places. In this analysis, as I've mentioned, we used undrained strength ratio, which was provided as 0.22 times a sigma prime, the vertical effective stress. And that's indicated by the nonlinear N on the soft clay formation. I then ran the circular search with all of the same conditions and just nominally ran 1,000 surfaces and got the same exact factor safety, 0.995. So that verified to me, based on the shear strengths and the geometry, that the search produced the same as the baseline individual surface. All right, then I chose to run. Oh, sorry, I missed a slide here. Let me go back. It's a little bit slow. I ran the ZRS auto search rather than the circle, but starting from the circle, and it produces a non-circular slip surface, as you see here. In that analysis, which I think is the true lower factor safety, I got a 0.960. And to me, that's a little bit too low for a case that's marginally stable at the time we're doing these analyses. So as Augusto presented in his presentation, I really wanted to see if the residual strength is, or let's say that the undrained strength ratio might be producing something lower than the residual strength, which doesn't really make sense. The residual strength should be the lowest strength that we're dealing with. So then I changed to a curved strength envelope using Tim Stark's correlation and using this equation, which is available in Geospace. This is actually a 3-parameter power curve with coefficients A, B, and T, with T being the tension component, or if you will, cohesive component. And if that drops to 0, then the equation just reduces to a 3-parameter power curve, which would be appropriate for the residual strength. Based on the strength or the index properties and data in the original report, I came up with a parameter of 0.25 and a B parameter of 0.85. And these are non-dimensional coefficients, which Geospace will handle dimensional or non-dimensional. This time I got a 1.018, which is, to me, a lot more realistic for a slope that is, at the time of analysis, marginally stable. So then I analyzed, again, using the ZRS auto approach and using the curve strength envelope to represent residual, but installing the 3 rows of drill shafts or piers. Then I got a factor of safety when I applied, in this case, I applied 14,000 pounds per foot in the out of plane direction, rather than that rather than initially assigning to an individual pier, because most of the time we may not have the size of the pier, the spacing, and that sort of thing to start with. So it's easier just to assume a per linear foot force in the out of plane direction. And then when the pier spacing and arrangements are determined, then that can be expanded to a per pier force. But in this case, we already had the piers defined at the 24-foot spacing. And I iterated the force until I got a factor of safety a little above 1.3, which I felt like was probably a minimum factor of safety that we'd want to look at for this condition in the limit equilibrium analysis. Okay, so then I ran a simplified 3D analysis that I can do in geospace, and with the input being a L over D ratio, which the D is the difference between the extreme ends of the slip surface vertically, and the L is the length of failure surface that I assumed in the out of plane direction. And so I got a factor of safety of 1.32, 1.432, and the ratio of the 3D factor safety to the 2D factor safety is 1.097, say about 10% increase for the 3D. This is a simplified method that assumes a shape factor for the bowl-shaped surface along the 3D dimension, and it's really just a good check. When I look at this factor of safety of 1.32 using the 3D approach, simplified 3D, and I look at the factor of safety ratio, it's about 10%. That seems reasonable. That just gives me some additional confidence that our 1.3 factor of safety in the 2D analysis is acceptable. So then we have to take the load that achieved our factor of safety and see how it pans out with a lateral pile analysis using L pile. So I chose the rightmost pier in the analysis, which has the greatest depth to the slip surface and should be the most critical case. In a real scenario, we would certainly need to analyze all three piers, and as has already been pointed out, there may be some local failure zones at the toe, at the crest, that bypass the drill shafts, and those cases would need to be analyzed as well and determined if additional stabilization would be required for those. But for this case, I just analyzed what I'll call the global surface, as you saw in the past analysis there. So in my approach, the slip surface elevation from geospace is transformed to the ground surface in L pile, with the pier extending above the transformed ground surface to the original ground surface. And the 336,000 pound force per pier load from the geospace analysis was applied as a uniform distributed load centered at the third point of the pier height from the bottom above the transformed ground surface, which I refer to as the free pier length. The load was distributed over a vertical distance of 9.5 feet, which is approximately equal to 20% of the free pier height. And again, it was centered on the third point. The curved strength envelope that was previously discussed was used to estimate an undrained strength for L pile. In discussions with the folks at L pile and I mean at Insoft, and looking at their PY curves that were developed over time, they feel like that the load tests were done slowly enough that in the vicinity immediately adjacent to the pile that we could estimate those strengths based on drain strengths. So that's what I've done. There are different things you could use. You could use the sand option in L-pile and use those PY curves. But actually, I found this approach to be more realistic and to match up with what we see in actual results in the field. So this is a diagram of how I set up the model. This, which is a ground surface in L-pile, is actually the slip surface in geostates, the limit equilibrium analysis. So we're going down to the slip surface and extending the pile above the transformed ground surface up to the level of the original ground surface in the LEM analysis. Then the 36,000 pound force is distributed over the 9.5 feet vertically and centered at the third point. I noticed in the analysis, I first ran it with 2.5 pier, two pier diameters of embedment, 16 feet. However, it looked to me like it was approaching a pushover analysis with the PY curves I was using for the weak rock. So I felt like it was prudent to extend it another half diameter, so I extended it 20 feet or 2.5 diameters. Now, some of the rationale for this model is that first, we see a lot of times in finite element analysis that the soil pressure on the upslope side of the pier is not, in fact, a true triangular pressure. It's more centered around with a stress bulb around the third point of the height above the slip surface. So I believe that more correctly models the load on the pier. And then we also many times have observed that after the pier is loaded, when the slope moves some additional amount, there may actually even be a gap that develops on the upslope side of the pier up near the top. And then removing the soil from the downslope side of the pier, as we've done here, is based on two considerations. One, that we have also seen and been confirmed by instrumentation as well as just field observations, that as the pier tightens up against this failure mass downslope, it's kind of really an uncoupled condition at the pier. And when the pier pressure on the soil mass on the downslope side, it will develop some soil pressure initially, but then the soil relaxes, and then the pier moves toward it again, and then it relaxes again until the pier resistance and displacement is mobilized, and then there's not much more soil resistance developed on the downslope side. Also, if you consider, we've already taken into account the shear strength along this slip surface downslope of the pier. So it's conservative and I think more realistic to not count it again in the L-pile analysis, because if we count on soil resistance above the slip surface, then we have to be counting on the shear strength along the slip surface again. So that's the rationale for that approach. All right, when we run the analysis using the conditions that I've described from the limit equilibrium analysis, we get about 3.2 inches of displacement at the top of the pile. And in this case, I'm saying that's acceptable. Of course, as I mentioned earlier, the factor of safety minimum and the maximum displacement would be established by the design team up front. And so if this was not acceptable, we'd have to go through another iteration, change the pile spacing, that sort of thing, to achieve what we need to achieve. So we're saying this is acceptable. So now let's look at the shear and the moment. So our maximum moment is about 102,000 inch kips. And the moment, what I call the moment utilization ratio, which is the mobilized moment or the developed moment, which is what we see here, divided by the ultimate moment, not the allowable, but the ultimate, to let us see what kind of reduction factor we're achieving. So that is 0.42, which indicates that we're not using very much of the total resistance of the pier in bending for this scenario. So then let's take a look at the shear. And the maximum shear is about 800,000 pounds, just a little less. And if we look at the shear utilization ratio, and both of those combined, are just considering them in one term, I call it the structural utilization ratio. So in this case, the shear is about 0.41. So again, if we had used the allowable shear, our factor of safety would have gone way up, but our displacement would have been much greater. So if we take a look in conclusion, if the stabilization had been designed on the basis of the allowable shear of the piers and limit equilibrium analysis only, a large factor of safety would have been indicated. But if the slope moved and actually loaded the piers to even half their ultimate shear strength, the system would have experienced a functional failure due to large deformation. And so that is what Ben alluded to initially. If we just calculate the shear capacity of the pier and plug that into our limit equilibrium analysis and achieve a factor of safety, we're totally overlooking the other three mechanisms, which would be the shear, the moment, and most often the one that controls is displacement. And so this approach has proven over the years to be very accurate based on actual observations in the field. And I think I've been involved in about 20 of these cases, and they all have performed within a reasonable range of this type of analysis. Certainly other approaches, soil movement adjacent to the pier and those kind of things can be done. Also, there are many other softwares or combinations of softwares that can do the same thing as MySlope Stability and as LPIL. But this is a rational approach that can be easily applied by a wide range of geotechnical offices and experienced personnel, and it provides a good rational solution that takes into consideration all of these aspects. So that's my presentation. And
all right. Thanks, Dr. Gregory, for a lot of good insights there, especially on how to, important points to consider and how you represent the load transfer between the slide mass and the pile. It's not trivial. There's a lot of different aspects of it that deserve some thought. And also pointing out that you need to carefully consider which PY curves you're using and how you represent the material, particularly if it's clay acting in a drained condition. Also, I want to say good job making the pile longer to avoid the pushover failure. As I pointed out, it's your job as the analyst to determine which mechanism is occurring, and if you're getting close to an undesirable failure mechanism, which pushover failure certainly would be, you need to do something about that as the designer, like making it longer. And we saw Gusto came to the same conclusion that it would be appropriate to make a longer pile. So excellent job. All right, we're now going to take a quick break. So we're halfway through the software presentations. There's 2 more, and we're right on schedule. So that gives us 15 minutes for this break. We'll resume the presentations promptly at 12:45 Eastern or 9:45 if you're on the West Coast. And we'll see you then. We'll be silent between then and now, but you can continue to type in questions into the question panel if you had any that came up during the last presentation. Thanks.
Very well. Okay, guys, welcome back after that short break and three great presentations. We will continue with our conference. Be sure to set your screen to full screen mode. And please, we've gotten several questions. Continue to type your questions on the screen and we will respond to them as they become available. Again, please note, no video or audio recording of the event, and you will be getting PDH certificates as well as PDF of the conference in a couple of weeks after the webinar. And with that, I'll give you our moderator, Ben Turner, for the second half of the conference. Thank you.
All right, thanks, Roberto. So we'll get back into the presentations now. We'll have the third presentation, which is from the rock science software providers. So we're going to be hearing from two rock science folks today. That's Sina Javan-Kostel and Jeff Lamb. Take it away, guys.
Okay, I'm gonna select these. Okay, thanks, Ben. Hi, everyone. My name is Sina Javan-Kostel. I'm a geomechanical specialist at Rock Science. I'm one of the developers of Slide software, and also I'm the expert modeler at Rock Science, 3D expert modeler. And I want to thank DFI for this opportunity. And today I have with me my colleague Jeff Lamb. Jeff, please.
Hi, yes, and I am a business development engineer with Rock Science, and my role is to help engineers find and use the right tools for their analyses.
Okay, let's start the presentation. We are Rock Science. This is our office in downtown Toronto. We develop 2D and 3D software packages for civil, mining, and geotechnical applications. For over 20 years, we have built geotechnical tools used by over 8,000 users around the world. We have over 50 employees at our head office in downtown Toronto, and more than half of them, they hold masters and PhD in civil and mining applications. Today, we are going to talk about the same problem, but we're going to use 5 different software packages. We're going to start with a slide, which is our 2D limit equilibrium analysis to find the factor of safety for the existing case. Then we're going to use RSPile to determine the allowable soil displacement that will produce the normal drill shaft structural mobilization. There is an integration between RSPile and a slide, so you can use RSPile inside a slide. I'm going to explain how. And next step is to determine the reinforced slope factor of safety with the 2D limit equilibrium using slide and RSPile. Then we're going to verify the results using our 2D finite element software, which is RS2. And after that, we're going to have some additional exercises, which are going to be interesting. We're going to go towards 3D analysis. We're going to use our 3D limit equilibrium software, Slide 3, to do the 3D analysis, limit equilibrium 3D analysis. And after that, we're going to confirm the results using RS3. So as you can see, there is an arrow between each two software. It means that there is an integration between these software packages. You can create a model in one, most of the time drag and drop in the other one and do the analysis. So we're going to show you some of the examples today. Let me introduce you these software packages a little bit more. This is a slide to our 2D limit equilibrium slope stability software. Basically, you can do any type of 2D limit equilibrium analysis, including support analysis. It has one additional finite element engine to do transient seepage analysis, and also we can do any type of statistical analysis, advanced statistical analysis, which is a spatial variability analysis, and I was the developer of this option in the slide software. Next software is RSPile. which we're going to use together with the slide. RS file can be used for 2D and 3D pile analysis. You can do axial and lateral pile analysis, group pile analysis to design cap even, and driven pile analysis, all in one software package. You don't have to have separate software packages for each of these type of analysis. And another 2D tool before I explain that, this is the integration between RS file and slide. Basically, the concept is you have displacements from the critical slip surface towards your pile, and you have the angle of these displacements. We take these parameters to RS file, we do the pile analysis, and we bring back the resultant forces from the pile. So if you select the type of support that you have as RS pile, this is the procedure that is going to be happening in the slide software. This is RS2, our 2D finite element software. It's a general 2D finite element analysis. You can do any type of civil and mining applications, including tunnel excavation, groundwater seepage analysis, and for the slope stability analysis, you can do shear strength reduction. And we're going to show you the results today. Go back to our modeling procedure. We had the DXF file, and this is the from a slide software. So we imported the DXF file into a slide. You can see that in a slide, you can define the external boundaries, material boundaries, water table, and supports from your DXF file. And after importing this in the software, the next step is to define your material properties. As been explained, we have 3 different types of material. The case that we are studying is a long-term drained material. We use more Coulomb for each of these materials. For the limit equilibrium method of analysis, we use Yambu and Spencer. The reason that we use these two, first, Yambu is a simpler method and it's faster, and it tends to give the lowest factor of safety among other methods. So it's a good for checking purposes. And Spencer is a more rigorous method, and we always recommend to use Yambu and Spencer together for the analysis. Next is to select the search method. That's the method that you can use to find the critical slip surface, and this is the important part of the limit equilibrium analysis. The traditional methods are circular methods, but nowadays for more complicated case studies, these methods, they don't work properly. So you need to go to more advanced methods. As you can see, our non-circular library is much more than our circular library. We just keep the circular for traditional purposes. In our non-circular analysis, we have advanced method called metaheuristic methods. Cuckoo search, simulated annealing, and particle swarm are our metaheuristic approach. And on top of these non-circular search methods, we have our in-house local optimization, which is surface altering optimization. And the combination of these two is going to help you to make sure that the critical slip surface that you're going to find is the lowest, weakest failure path. And how we can figure out, we compare the results with finite element analysis. And if you can get the same answer, it means that you use the proper search method, which we're going to show you today. So we did the analysis. First of all, it is not circular, as you can see. This is a non-circular critical slip surface. For the drain case, we got the factor of safety using Yambu method 1.02 and for Spencer 1.11. As I mentioned, the Yambu gives a lower factor of safety, which is a good check. These are all the critical slips, all the slip surfaces, and this is our critical slip surface. We can filter the slip surfaces to the ones that they are more critical, and we filter the sliding surfaces with a factor of safety of less than 1. And you can see this is the failure band, and the failure surface, the actual failure surface is within that failure band. So after finishing the non-circular analysis, we're going to move forward to the non-circular unreinforced case. we're gonna move forward to the reinforced case, and Jeff is gonna continue the presentation.
Thanks, Ina. So I will be covering the 2D integrated slope stability and power analysis model here and over the next few slides. So after we are satisfied with our unsupported results, let me just go to, okay, here we go. So the next step is to set up our slide 2 model with the reinforcing elements using the provided drill shaft configuration. Then we set up the lateral pile analysis using RS pile with the provided PY parameters and pile parameters. And then we went through the exercise of checking the structural mobilization along the pile length versus a range of soil displacements, just to see how much the pile can handle. And then once we have this number, then we iterate it through our slope stability analysis with that pile displacement as our upper limit. In order to determine the structural capacity of the pile, we use the ACI SP-17 procedure to obtain a nominal flexural capacity of 19,400 kip foot and also a nominal shear capacity of 1,964 kips. And these numbers go into the denominator of the structural mobilization. The numerators are calculated in RS pile along the entire length for the various soil displacements. So we started off by using 1 inch of soil displacement, and RS pile will automatically generate the lateral resistance envelope at that level of displacement. And we started with 1 inch because it is a common tolerable level of displacement that we've come across. But more importantly, it is within the range of displacement that we can expect to obtain realistic results. Higher displacements may fall into the category of larger stream problems, and the numerical programs that we are covering today are based on small strain theories. So the corresponding structural graphs, the structural resistance graphs, are also automatically generated for each of the starting depths. And note that I did not look at the starting depths in RS pile within this deeper kind of hard till formation because none of our critical starting surfaces go into it. So I left that part of the pile analysis out. And then, so now checking the maximum structural mobilization at 1 inch displacement in RS pile tells me that the maximum shear is developed at a depth of 56 feet. That number is 511 kips. Dividing that by the nominal shear capacity gives me a shear mobilization of 0.26. The maximum moment is developed at a depth of 61 feet when the starting depth is at 53 feet. That number is 3,014 kip foot. Dividing that by the nominal moment capacity gives me a moment mobilization of 0.16. So then I proceeded to check the structural mobilization with increasing pile displacement, or sorry, the soil displacement, until I reached some sort of a structural capacity. And the conclusion from this exercise is that we can basically rely on the structural strength of the pile along its length up to a soil displacement of 4.5 inches, where it will fail in shear at a depth of 56 feet, which is right above that much stiffer Red Lake Falls formation. And it is also worthwhile to note that it is unlikely that this amount of displacement will be called upon at that depth to stabilize the slope, but nonetheless, it's still a good exercise to determine the structural limits of the pile for our coupled analysis. So next, we're going to show how we can integrate the results from RSPile into Slide to give you that factor of safety. So if you go into support properties in Slide 2 and you go to support type, if you go below where it says pile, micropile, below where it says soil nail, you will find a support type here that says RSPile. And basically, that's just a lateral, that's where you're coupling that lateral pile analysis with your slope stability. Down here is where you will tell Slide which pile analysis file you want to point to. You also have the option to tell Slide which force application you want to use, the out-of-plane spacing, and then also the soil displacement. And we're also going to go with the 1 inch case here. And as the previous exercise showed, I can rely on this 1 inch for the entire length of the pile for the purpose of this integrated analysis. Okay, we don't have to worry about the pile failing on us once we have established that. So once the files have been linked, the pile resistance envelope for each pile, for each pile stratigraphy will be generated and directly integrated into Slide 2. And we notice that at a soil displacement of 1 inch, our factor of safety is 1.3. And if this is our target factor of safety, then it is the more likely that the geotechnical stability of the system that governs, because we still have, if you look here, we still have structural capacity left in our piles, right? I mean, we're mobilizing 0.1, so we still have 90% of that shear strength of that pile that we're not mobilizing yet. So in other words, if you are putting in the full shear capacity of the pile into your soil stability analysis, then perhaps you're not being realistic. Now, just to see what amount of displacement we would need to get to a factor of safety of 1.5, I ran a few more iterations, and I was able to hit that factor of safety with a soil displacement of 2.75 inches. And here we can still see that we still have lots of structural capacity left. Okay, so it is still the geotechnical stability of the system that is governing. And then I took it a few more steps further. So I went from 1 inch to all the way to 2.5 inch, and I kept loading up the displacement along the sliding surface until I reach the structural capacity. And as you can see here, as I load up the soil displacement, we are mobilizing more of that moment capacity than the shear up until failure along the sliding plane at 14 inches, at which point we have 60% of the nominal shear capacity mobilized. I think it is also worth emphasizing that this 14 inch is actually much larger than the displacement required to produce failure along a greater depth compared to the 4.5 inch that we saw earlier. So an additional takeaway from our Slide 2 and RSPile presentation, if you will, is that it is possible that the pile will fail at a lower amount of displacement at some other depth, other than the sliding surface that we are kind of honed in on. So best practice dictates that we check our results using another analysis method. And so we used our 2D FEM software, RS2, to do that. And it is a simple matter of taking the Slide 2 file, dragging and dropping it into RS2. The geometry will be imported directly. The program will automatically generate the mesh for you, elements, water table, everything. You get all of it. The material properties were imported as more Coulomb, and we used a plastic model for the soils, where the residual strength is equal to the peak strength. The pile parameters, E and moment of inertia, are calculated from the provided pile parameters. And the pile, we just modeled it as a simple liner with no slip. and then you hit the compute button, and then you can start getting the first iteration of your results. So, so just to check our unsupported case, right, to see if our unsupported results from from our 2D limit equilibrium and the 2D finite element matches, we compare this base case, and we are seeing a good fit because A, we are getting a comparable factor of safety of 1, and B, the critical sighting surface is also very comparable. So the 2D limit equilibrium surface is shown in red here, and the finite element shear strength reduction failure surface is shown by the green band. And then running the reinforced model with the failure surface going through all the piles gave us a shear strength reduction factor of close to 1.5, and this is also close to our 2D results. In terms of the deformation of the slope, as you can see here, it depends on the location. We do get various levels of localized deformation, but just to focus on the deformation along the pile, we are seeing a range starting from 0.6 inches at the base of that clay layer, the Huat formation, going up to 2.6 inches near the top of our weaker clay layer. So RS2 automatically generates all the steps for the shear strength reduction factor analysis, and also indicates if the pile has reached its structural capacity. This table is just a summary of the results I got from RS2, which is in agreement with the RS pile model, that the pile is mobilizing more moment as we continue to deform the soil. And we only brought the analysis to a shear strength reduction factor of 1.7, which actually produces a pile displacement of over 2 feet. And we don't think there's much value going beyond this displacement because that's when we start going into the realm of large strange displacements, which will require a different type of analysis altogether. So just going with this, it is once again seen here. It is the geotechnical stability of the soil of the system that governs. We have these areas of localized soil that are failing. And with that, I'll pass the presentation back to Sina.
Thank you. Okay, let's do some additional bonus analysis. Let's start with the statistical analysis. We have a very advanced statistical analysis in a slide software called spatial variability analysis. I'm going to explain what it is exactly. But before that, for the statistical analysis, we normally require some parameters. Let me see. So the first parameter that we require is the coefficient of variation of input parameters. In this problem, we assume that the friction angle of the soil has the 15%. This is a typical number of variability. And we investigated 2 different cases, one with a spatial variability and one without a spatial variability of soil properties. To define the spatial variability, we required a parameter called spatial correlation length. That we didn't have it for this analysis, but since we had CPT data, we could measure it. This is an algorithm that is written in a slide and it's going to be released in future, but we already had it, so we used it to measure the vertical spatial correlation length of each layer. So for the first layer is 1.8, second layer 2.4, and third layer 5 meters. These are just vertical. We assume that in horizontal direction there is no spatial variability, which is a typical case for most of the case studies. So assuming these numbers, we defined our spatial field. So what is a spatial variability? A spatial variability means that your soil properties depends on the location of the soil property in the soil profile. So assuming that the soil is homogeneous and it's the same value along the soil profile, it's a little bit too conservative. So what we did, we defined these correlation lengths for each layer, and you can see that the blue regions, they are weak material, weak regions, and as it goes to green and yellow, the material becomes stronger. So it's not homogeneous anymore. We did about 2,000 simulations. We have some search algorithms, simulation algorithms called response surface method in the slide, which is very fast. You don't need to do all the 2,000. You only need like 30 of them, 40 of them to do the analysis. Let's compare the results. We started with the unreinforced case. For the case that, first of all, we look at the deterministic factor of safety. They are exactly the same. This case is with no spatial variability, deterministic factor of safety. We got the probability of failure of 27.8%, which is not a reasonable number for this factor of safety. But considering a spatial variability of soil properties, this number dropped to 7%, which is much lower. But still, it means failure. And we expect that we have some failure with this factor of safety when we do the probabilistic analysis. So we pick the case with the spatial variability, and on top of that, we add reinforcement layers, which is possible in the slide software. So this is the case with 2.75 inch of displacement for soil. So you can see that factor of safety is 1.53, the same that we found in the deterministic analysis, and we got the probability of failure of 0%. In each simulation, our spatial field changes, and this is one of the simulations that we got factor of safety of 1.33 almost. If you look at the critical slip surface, you can see that it goes through the blue region and goes up. This is what I mentioned about the search methods and our surface altering optimization. It's smart. It finds the most critical failure surface that goes through all the weak regions. So if I run the finite element analysis for this example, the same region is going to be found by the finite element analysis, which matches the result of limit equilibrium. Then we moved forward to the 3D analysis. We saw in the pools that only a few % of people use 3D analysis. Maybe I encourage you to do more with these examples. So we used 2 different methods to create our 3D geometry. The first method, at the beginning, we had 3 sections in 2D. And we wanted to use these sections to create our 3D geometry. First of all, I did not extrude to create these sections to create the 3D geometry. This is the actual 3D coming from 3 2D sections. So how it works, we use the sections of 2D, and also we had some boreholes, and also we defined some additional boreholes from our 2D profiles that we had, and combining these, we created our 3D geometry like this. So these are our 3D sections. So this is one way of doing it. After that, we got the elevation contours from the committee, and these are the actual contours of the profile. So this is another way of creating geometry. We use these contours, and we created a surface using these contours, and also we use our boreholes to create our geometry. So this is the real 3D. This is not extruded. This is coming from the elevation contours. So we ran the analysis for both cases. This is the case that we use the 2D sections to do the analysis, to create the 3D geometry. And you can see that for the unreinforced case, we got the factor of safety of 1.27. If we look at the safety map, you can see that this is the failure zone, and as we go further, the slope becomes safer. If you look at the results of the actual 3D coming from the elevation contours, you can see that the factor of safety is 1.17, which is lower than the case that we use 2D sections, because this one is more accurate. So the first lesson is, if you use the actual contours, you may get a different factor of safety, which is more realistic. The second conclusion here is that 3D and 2D, most of the time, not always, 3D gives a larger factor of safety. But how much larger? We don't know. It depends on your 2D section, where you cut the slope. It depends on your type of geometry, and depends on how you create your 3D geometry. So all these are factors to affect the factor of safety. It can change from 5% to maybe 20%. I haven't seen something like with 40% changes. Maybe if you extrude or do something, you get 40% changes. But normally, this is it has a lower range. So you can look at different contours. This is the factor of the friction angle contours to look at your slip surface and see how many materials your slip surface is touching. You can see that the red region around it is one material, and the blue region is the weaker material. So it shows that our slip surface goes through the weaker material, most of the slip surface. And you can bring your critical slip surface up and look at the material below it as well. This is a slide 3, so a limit equilibrium software. So what happens, what is the difference between our 2D and 3D results? So in the slide 3 software, you can define 2D sections and run the engine of 2D software as an add-on in the 3D software. So we ran the 2D engine for different sections, and for section A, we got the factor of safety of 1.09, which is very close to the one that we had in our 2D results, which was 1.11. And for section B, we got 0.88. As I mentioned, there's an integration between a slide 3 and RS3. RS3 or 3D finite element software. They share the same type of geometry. So this is the geometry that I created in the slide 3 software. I just imported to RS3, meshed it, add restraints, and I could run it. That easy. So I ran the 3D finite element analysis, and these are the contours, 2D contours. And the gray region is the region for the critical slip surface of the slide 3 software. And if you look at these contours, you can see that they match perfectly between 3D finite element and 3D limit equilibrium. And also we got the SRF of 1.16, which is exactly the same as our slide 3. As I mentioned, if you use proper search methods, you should get the same answer in the finite element analysis as well. Then we added the support pattern based on our 2D pattern that we defined. Again, we used the case with 2.75 with soil displacement. There is no integration between a slide 3 and RS Pile, but you can get the output of RS Pile software and define a user-defined support type in the slide 3 and import the output of RS Pile as user-defined properties. So we have distance and we have capacity. So we got the information from RS Pile and imported to a slide 3. We defined the pattern as a horizontal spacing of 24 feet and vertical spacing of 40 feet, which is the pattern that we had in the 2D model. And we created this reinforced model. And if you look at the results, the factor of safety goes up to 1.6. In 2D, I think it was 1.55. So it's higher, but not that much. It's a little bit higher than our 2D case. And if we bring the slip surface up, you can see these are the reinforcement supports that they have intersection with our critical slip surface, which intersects it, most of them. So as a summary, we found the capacity for different soil displacement in RSPy. We imported them into our 2D software. For 1 inch, we got factor of safety of 1.3. For 2.75, we got factor of safety of 1.5 in a slide. We take this second case to RS2, we got factor of safety of 1.5 and in 2D, and we imported the same case. We created a real 3D geometry, and we got the factor of safety of 1.6, which all match. If you have any questions, feel free to ask, and we're gonna come back and answer your questions. Thank you.
Okay, thanks, gentlemen. So there were a couple questions that came in. I assigned them to you guys. You can take a look for kind of a sneak preview, but thank you for the presentation. A good contrast and comparison between limit equilibrium method and more robust numerical analysis methods. And I think that's going to be one of the focuses of our Q&A session, is how to decide as a practicing engineer when to use or what method is most appropriate. All right, so now we have our final presentation from Murray Fredland from Bentley. And after that, we'll get into the Q&A session. So take it away, Murray.
Hello, everyone, and glad to be here. And yeah, I'll be presenting on behalf of Bentley, analysis of embankment with piles. And it's just, there we go. Oh, let me go back one here. Yeah, as said before, my name is Dr. Murray Fredland. I'm a senior strategic advisor of geotechnical with Bentley Systems, and happy to be presenting here today. Happy to be part of Bentley as well. They've recently expanded their portfolio with acquisition of Kinetics, Plaxis, and Soil Vision, and we've got a great geotechnical team going alongside of the GINT software. So what I'd like to talk to you about today is go through a little bit of the problem definition. I mean, Ben has already walked us through really what it is. We'll talk about the unstabilized condition and how to calibrate to that. We'll talk about the stabilized condition with piles and kind of walk you through the different ways we can analyze that, and then provide a little bit of a summary at the end of what we can determine from that. So as mentioned, we have the overall plan view of the site. We have 3 cross sections, A on the right and then B and C. And we have some measurement points for CPTs and piezometers. And for the case of the study, we're focusing on cross section A, as that's what was provided to us. And then for the 3D analysis, we'll pull some of the 3D data together and show you how that changes things. So, and just in terms of the analysis tools, we're going to compare SV slope, which is a limit equilibrium product. There's no deformations considered with LEM. We should remember SV slope can be fully coupled with finite element seepage analysis and stress, as well as Plaxis can. And we're taking the different approach with Plaxis, FEM of shear strength reduction. So then we're weakening the soil until the piles incur a moment in shear stress maximums if they do. And we can model the piles by either elastic or plastic response. And just a reminder that when we're doing this method, we get deformations that largely can be considered fictitious because we're artificially weakening the slope. So if we move forward and just look at the unstabilized condition first, calibrate it to it, really what we're trying to do is what material properties, drained or undrained, produce failure. And we're going to assume the water table is correct at this time and assume no trigger mechanism. So here are the material properties for the different materials on the site that were provided to us. Just note at the hot formation clay, we have both drained parameters, friction angle of about 15, and undrained of about 0.22 parameters. And for the pile, we were provided just the compressive strength of concrete and the rebar pattern in the pile itself. So I first went to a consultant friend of mine at a consulting firm, and he had a spreadsheet. He plugged in the numbers, and we came up to about, for moment capacity, about 9,000 kip feet, shear capacity of 694 kips. And we wanted to be a little more sure about this, so we plugged the numbers into the Ram Elements Bentley structural product and built the pile with the rebar and the concrete in the product, and came to more of a moment capacity of about 12,000 kip feet and approximately 1,200 kips shear capacity. And as a side note, we could also rebuild the pile in Plaxis and analyze it with no rebar, and we came up to about a 7,700 kip feet of moment and 1,300 of shear capacity. So just bringing out how you actually even analyze your pile capacity in terms of shear and moment capacity. There's a little bit of variation on your methodology, whether you look it up from charts or whether you analyze it in more of a structural package or what you do. And so let's move on here. We used largely the reinforced values in most of the analysis. So if we just start off very straightforward, unstabilized condition, we analyze it with SV slope, limit equilibrium, without piles. We've modified the geometry to move the surface up to approximate pre-failure conditions. As we noted that we were given post-failure geometry, and it actually makes a difference. The location of the slip surface matches extremely well, and we just overlaid the site profile drawings on top of the modeling results. It's a feature in the software. And the undrained analysis produced about an undrained strength ratio of about 0.25 with a factor of safety of about 0.98 with the GLE method. And so we're able to get excellent matching with the slip surface in 2D. We move forward here and do a drained analysis, same exact problem. We get a friction angle of about 15 degrees, the factor of safety about 0.98 by the GLE method. And again, the slip surface match as well. And so just for interest, because at the site, I mean, one of the potential influences is climatic. And you could get into detailed climatic modeling with SV flux and calculation of actual evaporation. But we didn't do that in this case. We just moved the water table up plus or minus 9 feet from the location that it was given. And the percent change, if you raise the water table, your factor of safety goes down about 7.6% is what we found. If we lower the water table, factor of safety goes up about 5.8%. So just to give you an idea of the percent changes of just the water table on the system. So we also analyzed this in Plaxis using shear strength reduction, and we found very comparable results. The factor of safety was 1.12, which was exactly the same factor of safety we got from LEM if we used the post-failure geometry, which we did in Plaxis here. And you can see a little bit of the predicted slip surface creeps uphill, and that's an artifact of the modeling the post-failure geometry. And what's interesting is both the factor of safety and the location of the slip surface, if you modeled apples to apples with the two software packages, came out to almost be the same. And we were able to do that. We have a new feature in the software where you can flip the geometry from SV slope to Plaxis and back, so it's very easy to transition between the two software packages. And so we'll keep going here. And just as a note, what we did for interest's sake is we took the 2D profile, and you can pull it out in SV slope and extrude it in the third dimension. So it's not representing realistic site conditions, but you are improving your failure surface from modeling basically a cylindrical type of 2D failure to modeling an ellipsoid in 3D. And if you do that, keep everything else the same, or keeping the water table the same and everything else the same, basically you get a friction angle in the drained analysis of about 12 degrees, which is a 20% reduction in the factor of safety to keeping the factor of safety still at 1. So just a note, and the location of the slip surface was still roughly very similar here. We took a cross section down the middle, sliced down the middle of the failure. And just a note that these models, if you have a back analysis, you know the location of the failure, you should be modeling these as 3D because they're non-conservative if you model them, just do a back analysis in 2D. So then what we did is we built the problem in 3D for a further, a true 3D is what I would say. And how we did that is we took the 3 profiles, we digitized them out of the engineering report, and then we used a new tool in the software to essentially stitch the profiles together and find common points and put splines between the profiles, so we get a little bit more realistic 3-dimensional model. And then we took the original ground surface. There was a little bit of discrepancy, is what I would say, between the different topologies. Using what method, you got a different surface, but we put this in here. We put the piezometer results in 3D, and we found that actually in the real world data, there's slightly artesian conditions that develop down here. So this upper blue line is the from the result of the piezometers. The lower blue line is the water table of the Red River. And so you develop slightly artesian conditions. And if then you do, we did a multi-plane analysis and swept it around the slope. So we can do that spatially, and you get a 3-dimensional contour of where your factor of safety is lowest. In this case, right about here, and we got the factor of safety dropped to about 0.69 from about 1.0. So if we were doing this for Sirius, we would then try to get this back to about 1.0. So then it just highlights that there's a few different variables. When you start to consider and bring your model into closer alignment with the actual site data, you learn things, and your model becomes a closer twin of reality, really is what happens. So we didn't pursue this very much further. We also modeled this situation with Plaxis in 3D with shear strength reduction. In this case, we didn't model the artesian conditions, and we got a 3D factor of safety of about 1.12, friction angle of about 15. And so, and not exactly apples to oranges, so it's a little hard to compare, but just to show that that approach can be done as well in finite element as well as LEM. And largely what we've found is that if the problems are posed exactly the same, you'll get pretty much the exact same results in the 2 packages if you're assuming the same failure mechanism and everything. So just a summary of the unstabilized conditions. Using the original pre-failure surface geometry makes a difference. The slip surface determined through searching is close to actual, which is always encouraging if you're doing a free-form search, and it actually hones in on the real-world failure surface. The undrained parameters can be seen below for drained and undrained. And again, just to highlight that we should be doing back analysis in 3D, because otherwise you see the danger is if we do it in 2D, we're getting an overestimation of material strengths, which if then what can happen is if you use those higher strengths to design your remedial solution, then you're overestimating the actual strengths that have actually been noted on the site. So 3D analysis should be used for back analysis where possible, where we have data. So if we want to move forward and look at the stabilized condition prediction, and we want to look at what factor of safety will a reinforced solution produce, we're going to assume the water table is correct as provided to us and is non-artesian. As mentioned, I won't spend a lot of time, but this problem is uniquely complex in that there is a lot of potential failure mechanisms. Your pile can fail in shear. It can bend in moment in multiple locations, depending on the geometry and the stresses in the system. Clay can deform around the piles, leading to excessive deformation, or the pile can push over. And so these are very hard to predict, as Ben brought out ahead of time, what the failure mechanism might be. And that's why we have great software to analyze this. So what I'm going to do is walk through this simple to complex and just start simply, move to more complex models. If we just analyze this, set this up in 2D with limit equilibrium and SV slope, we actually get a small superficial slide, which is also replicated in Plaxis down by the river. And it's just worth noting because it's actually real and it is a true minimum. However, I mean, we're not considering 3D analysis or unsaturated shear strength, so likely that's why in reality it hasn't failed down here, but it's something to consider anyway. So what we tend to do as engineers is eliminate that because it's not a high volume, and you can just tell the software to largely ignore it, which we did in future analysis, but it's worth noting. So we eliminated that small superficial slide. You get the larger slide that we're more concerned about in terms of through the piles. We've modeled all the piles as passive, and we've assumed shear failure in the piles, which is like Ben said, is an assumption. If we do that as a reference point, we get a factor of safety of about 1.55 here. There's a slight inconsistency in that really you have to realize these 2D models are plane strain models that are set up. They are modeling a 1 foot thick wide section in the third dimension, and really we have 8 foot piles. So that came up in the discussions. Well, can you truly model 8 foot piles in a 1 foot section? And really what we realized when we set up the model, what we did is we put in the full shear strength or shear resistance of the pile as if it was an 8 foot pile applied across a 1 foot section. So it turns out that that's a very reasonable way to pose the problem to the software, provided that you assume that the piles are failing in shear. So as a small note, we also have active and passive zones roughly of this failure. You could give an argument that the upper pile is more in active failure and the bottom two are closer to passive. So we did that, and the factor safety jumps to about 1.68, just in terms of interest. So all of these are modeled as a pile spacing of 24 feet, and we still are not fully there, although we're moving towards a more accurate situation here. So then we went to Plaxis and modeled this with embedded beam elements and used the piles as embedded beam elements here in Plaxis. Got a factor of safety of about 1.4, and with a drained clay formation, shear strength of about 15 degrees. And you could model this with many different types of drained or undrained behaviors. We just used drained in this case for the sake of simplicity. So move forward. There we go. Oh, there's a little bit of delay on that. Let me go back one slide here. So if we plot our factor of safety versus total displacement, here's the case for the original ground. We're about 1.12 in terms of factor of safety. These curves are interesting to note from the sense if you model elastic piles, you get quite a malleable type of behavior that takes a lot of deformation, and you don't really achieve a plateau until very high deformations. If we model with elastoplastic piles, the factor of safety drops from 1.4 to 1.32. You have a little more failure, but you're still up around, you realize, around 10 feet here of total. This is total slope or toe displacement, which is the maximum displacement noted at the slope here. So we've dropped from about 1.4 roughly to 1.32, given an increase in our ability to model the piles. So let's keep going down here. And if we look at shear and moment, however, we're actually achieving, if you look at the bottom orange line, this is what it is you're plotting the shear and the moment over the maximum. So really you've achieved failure once you pass 1.0 on this graph. And what it tells you is that you're not actually achieving shear failure till very high displacements, which are in the realm of arguably large strain, which changes your analysis. However, you're achieving the 1.0 roughly at about 7 feet here of total or of toe deformation. And what it clearly shows, what you can ascertain from this, is that moment failure is achieved before shear failure of the piles in this situation. So that is your failure condition. However, it is at a fairly high deformation. So if we change the piles to elastoplastic piles, now we're seeing that we don't ever achieve shear again, failure of the piles, and we achieve moment failure of the piles at quite high displacements. And so this is using bending moments. So just a line of elements in 2D essentially is what we're doing in this case. So if we move this up to 2.5D, which really 2.5D is just pulling the model out in 3D a unit width, 24 feet in this case, and modeling it like that. So really you're not changing your failure surface is still a barrel or a cylinder that's rotating. However, you're modeling, the attempt is to model the piles a little bit more accurately. So what happens if we now move to this scenario? So first with LEM, what we did is we pulled it out in the third dimension, 24 feet, and we modeled the piles as 7 foot by 7 foot square concrete with more Coulomb shear strength properties. And so specific dimensions, the slip shape is assumed to be very much like 2D. There's no shear resistance on the sides of the slip, and the ellipsoid shape is set to be very extensive in the third dimension. So really what you're doing here is you're creating an analog to a 2D analysis, really is what you're doing, only we're increasing the accuracy of modeling the pile dimensions. And not surprisingly, the factor of safety produced with the 3D analysis is almost identical to 2D, which just essentially proves that your 3D is continuous and a good representation of your 2D analysis going forward into 3D. But again, with this, to criticize this analysis, you're still assuming shear failure of the piles in this analysis. Only now we're getting more fancy with it. So if we model this now in Plaxis, now we can start representing the piles as volume materials with interface elements and putting in rebar and representing the pile and the soil structure interaction in more detail. So we can model the piles as elastic behavior or elastic plastic volume piles in this case. Our shear strength, our slip surface is still largely the same as 2D in this case. So if we look at this graph, I find this interesting. Here is our LEM analysis, 1.57 for comparison. If we model the piles in 2.5D with FEM, elastically, we get about 1.58, which is almost the same. Here is our original factor of safety with unreinforced at the bottom, 1.13. And here, if we model the piles as plastic, elastoplastic, what we have is a peak coming up here at about 1.5 feet. And what you're essentially watching is the first pile failing. Then this next hump is the second pile going into plastic failure by moment, and the third pile. And then you stabilize as you deform more at a factor of safety of about 1.37. So you're able to because you're weakening the soil, you're keeping the pile strong essentially here, and you're noting the progressive failure of the system. So very interesting. And this just shows a visual of the piles bending over and getting where the plastic hinge is, which is about 14 feet down into the bottom red clay formation. So, and you can also plot in Plaxis, you can plot the moment diagrams and shear diagrams, maximums for the piles at any depth. And just bring out a few things. You'll notice that in the top figure, as you increase, we're increasing deformation from left to right. And as you increase the deformation, what you're seeing is that up to 1, 2, 3, 4 picture frames, you're getting a maximum moment. And then the pile goes into plastic failure and it all of a sudden decreases down here and you lose your moment strength. So it tells you the location, your approximate peak. And here you're seeing the shear is down in the red clay formation, maximum shear, and you can see it developing differentially in the 3 piles, which just interestingly enough to bring out that, I mean, in a failure like this, or it's not a failure, but in a scenario like this, you will have different responses from each of your piles depending on where they're located spatially. And you can map that through with the Plaxis software. And that's one of the benefits. I think you can model the detailed soil structure interaction. So if we plot again the moments and the shear in terms of capacity at 1.1, you can see that we reach capacity, moment capacity of the piles at a deformation about 1.5 feet here, and we don't really ever achieve shear failure of the piles. So just like Ben theorized in his first presentation. So if we look at 3D though, what does a factor of safety produce and how is this different? And we're going to assume the water table is correct, assume no trigger mechanism. And if we just do something simple first, we pull it out in 3D. And so the advantage here is we're improving the shape of our slip surface. And what SV Slope has is the ability to search both elliptical and fully non-elliptical in 3D for slip surfaces. And you're seeing that shape develop here in 3 dimensions. And you're just putting piles every 24 feet all the way along this extruded problem. So if you improve your representation of your slip surface is really what we're doing here. You jump up to about 1.8 in terms from about 1.55. And so we're just, again, simplistically, we're changing one thing at a time. Now, if we take the full 3D problem, which what we did is we extruded we built it with the 3 cross sections, used splines to stitch it all together, as I earlier showed you. And use this case is a little different because we're using the real field data. So you have artesian conditions down near the toe of the slope, and you're putting in the piles. So we swept the piles through here in an arc, 3 rows of piles. You can do that automatically in the software, and we put them down to the noted depth, gave them pile the shear strength, and basically just set this so we're assuming shear failure, of course. It's noted that the geometry wasn't perfectly complete for this site, and so we had to make some assumptions in terms of the range of data. However, and then we ran a multi-plane analysis and searched across the slope, and interestingly enough, you can see it converges to a non-elliptical shape that is got sheer steeper side slopes, and it did that to try to avoid engaging more piles on the edges here. So it's performing very adequately. It was also moving a little bit to the left here, or to the right, sorry, in terms of your most critical location, but you're at about 1.9 in terms of your 3D factor safety for this case. So as you increase your representation of your model, I would say you get closer to reality. So in terms of field deformation, you really require an actuating deformation. It's hard to say, like, if we implement this design, what is our deformation? You need an actuating mechanism because you need a change in shear strength to determine any kind of deformation with your analysis. So in this one, we just put force on the piles laterally and deformed them, I think approximately 1 inch. Here, applied the loads in a 2D model. You can chart the shear stresses that develop and the resulting deformation of the piles in the finite element analysis, and consider the interaction of the soil. But really, this doesn't, you have to realize this is a deformation which may hit a deformation limit. It does not really affect your factor safety. There's marginal impact on your factor safety of starting from a deformed case as opposed to starting from no initial movement. So it affects your deformation criteria for field performance, but not your factor safety in a big way. So in terms of a summary of what we found through this interesting study, really pre-existing conditions, your factor safety is 1.12 in both LEM and FEM. If you do a back analysis, you can determine properties for drained and undrained. If you do a 3D analysis, you're getting about a 20% reduction in your material properties in this case. So just to answer some of the committee's questions that they provided to the analysis group. What failure mode is controlling? Really, moment or flexure failure of the piles is controlling. What is the computed stabilized factor safety? The values range really between 1.37 and 1.89, depending on how you analyze this situation. And it's really governed by the moment. And what amount of slope displacement is anticipated for the factor safety computed in Part B? This should be 1.5 feet, roughly, is the approximate deformation. However, we just have to realize that that's fictitious. What amount of actual slope displacement actually anticipated? you would need an actuating mechanism or some kind of stress change to, you need to push on the slope, lower the water level, do something like that to compute an actual field displacement. So in summary, 2D material properties back analyzed are non-conservative. We can improve our analysis going to 2.5D. 3D analysis improves your model, your accuracy and your model insight in this case. Deformation analysis, you must assume a deformation in this case in the absence of a trigger because you have no stress change. So it's a difficult modeling scenario. And I would bring out, this is interesting, I find, to summarize like this. If we, as Ben suggested at the start, we go from LEM to FEM where we're including detailed soil structure interaction with piles, we note about a 12% reduction in your factor of safety overall. However, if we go from 2D to 3D, there's about a 22% increase in your factor of safety. So you have a net increase. I mean, there's also a case to be built that we should be modeling these things in 3D as opposed to 2D because we have a bigger potential impact on our calculated factor of safety. And just to bring out, I think the ultimate analysis in this case is really going to a 3D FEM where you're including all the soil structure interaction and the piles and the moment of every pile in the analysis. We didn't have the time to go there, but this would be the ultimate analysis to go to in the future. And so lastly, here's my contact information. This is an enjoyable discussion to have. We've had a great time kicking this around even internally in the office, and I would be happy to hear from anybody that wants to have a discussion about this. And as well, here's a link to further resources with the Bentley team and the suite of products. Thank you very much for your time.
All right, thank you, Murray. So thanks for to all of our software providers there for putting those presentations together and putting the time in. We're going to transition now to the question and answer session. So there's still time. You can type a question in to the question panel over on the dashboard, and then we will discuss those. We're going to go till about a quarter after the hour here. I'll just mention too that if we don't get to one of your questions, they will still be answered eventually, and the transcript of the Q&A will be provided to you along with the PDF of the presentation. So first, to kick it off here, I just want to make some concluding remarks that were the takeaways from me after watching the 4 different presentations, just sort of some big points. And I think these will answer some of the questions that came in or maybe spur some more discussion. The first one is, hopefully if you weren't already convinced of this, you now see that you simply can't consider the deep foundation behavior in the slope stability analysis without explicitly considering how the deep foundation element is going to behave on the structural side. You have to quantify at a minimum its nominal moment and shear strength, but also some analysis that takes into account the relationship between stiffness and deformation and strength and mobilized resistance, etc. So that's just the reality. You can't separate that out. A second takeaway is, as Murray just said explicitly on one of his slides there, I noticed, limited equilibrium slope stability analysis, by definition, does not include displacement. That's absolutely true. When you calculate a factor of safety, it tells you nothing about how much displacement will occur in the slope to get you to that point, okay? But as you've seen, it's impossible to quantify the amount of resistance that the deep foundation provides without explicitly considering displacement, because the way we do it is incrementally displace the ground relative to the pile to study the mobilized shear force and also to monitor what other mechanisms might occur. So I think that's important to keep in mind when we talk about representing the structural support in our limit equilibrium slope stability analysis. Right off the bat, we're kind of breaking the rules because we can't divorce the displacement side of things from the amount of mobilized resistance for the structural elements, and yet we're bringing that into an analysis where we're saying from the get-go we know nothing about displacement from these results. So keep that in mind as a designer and just kind of a big picture concept. The third point is that all the software providers concluded a couple of things. There were some common findings between them. One is that a moment failure would occur before a shear failure. I think that was universally agreed upon across the board. So that just highlights, again, and reinforces the idea that if you went into this particular problem and assigned the structural shear strength to the deep foundation elements or as the resisting force, you'd be wrong, potentially by a large margin. The flexural failure would occur first as a strength limit state. But in addition to that, all the software providers concluded that you would actually reach a practical limit of displacement beyond which further displacement would be excessive and would be detrimental to the slope or the structure that it supports. In this case, the actual slope supports a highway. And they all concluded that after a few inches of displacement, there would be disruption to the functional operation of the facility, which is a perfectly reasonable conclusion to come to. And that occurs prior to reaching a strength limit state, either geotechnical or structural. So I think that's important to keep in mind. In my presentation in the beginning, I really focused on strength limit states, but you could very easily face a situation where you reach a limiting displacement prior to mobilizing one of those. So you'd be putting an even smaller cap on the amount of resistance that goes into your slope stability analysis. And I think this also highlights an important point, and many of the presenters made comments, and they all kind of phrased it differently, but in effect, they were all saying the same thing, which is that factor of safety by itself doesn't really tell us the whole story, particularly in a slope stability analysis where we're trying to bring in the resistance or a stabilization scheme, whether it's deep foundations or anything else. It's really important to put this in the context of expected displacement and performance criteria. And so I think probably the most important takeaway, if you are an owner or a consultant that represents an owner and helps develop requirements or specifications for slope stability problems, particularly on behalf of public agencies, if you're just prescribing a factor of safety requirement, you're not really going to capture the whole picture of what's going on. It's important to also prescribe a performance limit or amount of displacement that can be tolerated. You could argue that that's all you really need to prescribe, because that's what it determines the actual or describes the actual performance of the slope. But you might consider doing that in addition to a factor of safety that correlates directly to a strength limit state. So just kind of some food for thought. And I'll point out that in that regard, the LRFD framework for design lends itself really well to this scenario. Even though I think it's geotechs, we can sometimes be wary of LRFD, or it's unclear how to implement it in something like a slope stability analysis where we're used to talking about factors of safety. It actually lends itself well here because LRFD already has serviceability limit states defined as being separate from strength limit states. And with that, I'll mention that I meant to say this before, but the DFI committee funds have funded a report writing effort that's forthcoming. It's led by Eric Lohr to discuss exactly this topic, factors of safety as applied to structural resisting elements in slope stability analysis. So that's coming sometime in the near future, and will provide more insights into this topic. Okay, with that, I think we're going to jump into the questions. And actually, I'm going to first bring one up that is based on what I was just kind of describing. So the question is, geotechnical stability analysis is based on factor of safety, while modern structural design is based on LRFD, exactly. Once the required stabilizing pile load is calculated from geotechnical stability analysis to achieve a target factor of safety, should that load be subjected to load and resistance factors for verification of structural capacity, or in other words, to complete the structural design of the element? Great question. I hope that this will be addressed in detail in the forthcoming report that I just mentioned. My opinion personally is that if the factor of safety you're calculating is above 1, say it's something like 1.4, the force that it takes to get to that point in the pile, a shear or moment force, is effectively factored. The factor of safety is like a proxy for the load factor. So I would not apply an additional load factor on top of that. but you should still apply the structural resistance factor, like 0.9 for moment, for example, to be consistent with the overall LRFD framework. It's worth pointing out that those factors are not calibrated for this particular application, but that would be my 2 cents on it. Do any of the other panelists or software providers want to weigh in on that topic? Should you apply a load and or resistance factor to the results that you discussed today to complete the structural design?
From my perspective, this is Augusto. I totally agree with, oh, should it turn on the camera? I totally agree with Ben's comment. I would not apply an additional load factor to what I'm getting from the stability or soil structural interaction, but I would still apply a partial safety factor to the material in terms of the cross-section verification.
Yeah, thanks, Augusto.
I wanted to add a comment as well, Ben. Again, I agree as well. There was a question regarding the methods that we use in a slide, passive or active. For the support types that we have, we use the passive option. It means that the support doesn't apply any force at the beginning, but the factor of safety is going to be applied to the soil and support together. So when factor of safety is applied on both, it means that you don't need to add an additional factor to your support. So this is confirm what you said.
Yeah, thanks. Right. So there was a question about method A and method B and what they mean in slide, and you're addressing that topic there. And Dr. Gregory, I know you have some input on that probably because the terminology comes from your book, Duncan and Wright. Do you want to weigh in on that?
Yes, and actually we're kind of moving away from that terminology because it's been somewhat confusing. But whether or not the factor of safety in the limited equilibrium analysis is applied only to the soil or to the soil and the structural element, that's what we're talking about. So factor of safety applied or not applied to the structural element. And if you apply the factor of safety in the limited equilibrium analysis to the structural element, the reinforcing element, and if we go to the old terminology, that's method B. It's a moving target. You know, you can't factor your structural element independently because every time you change your capacity or anything, you have a new factor of safety, and that's been applied to the element. So, but if you're looking at ultimate capacity, considering ultimate capacity of, in this case, the piers, then you have to consider what resistance factor you would apply to it and reduction factor and so forth, because the factor of safety that might be suitable for the slope's not necessarily the same as you would apply in a reduction or a load factor. So I think that has to be considered. I generally agree with what the other two people have said, but I think you have to keep in mind what ultimately what factor of safety has been applied to the structural element, including considering load and resistance factors. Also, in some cases, until we can move further along in the profession, we run into regulatory requirements where it's prescribed to us, and we don't have any choice other than to do what the regulations say for particular reviewers, as long as we're use a safe approach to what we do. So I think it's a really good question, and hopefully the report will answer some of that. But so that's my take on it.
Very good, thanks. Okay, kind of switching gears here, there were a number of questions that asked about how do we determine if a flow around failure is happening, and then there were some variations on that. How do we do it for different types of soil? So it's an interesting question, and I think perhaps the most interesting part of it is if you're doing a 2D analysis, whether it's limit equilibrium or continuum modeling, and you're effectively scaling things per foot out of plane, how can you determine whether or not that flow around failure is occurring? And then kind of a related topic, how do you know if your piles are too widely spaced out of plane so that you're getting flow between them and not what some people might call arching? Whereas in your analysis, you're uniformly scaling per foot out of plane. So you could be wrong there. How can we get some insight into that? Anybody can go ahead and answer.
Okay, I'm gonna try to start. As far as the flow around, if you really want to model flow around the body, probably we are not able totally to capture the interaction with the approach that we are using, because again, Jeff, I think, was mentioning small strain approaches and continuum approaches, and we can kind of have a feeling, at least in my mind, if we get a lot of displacement and we are not able to mobilize the structural reaction significantly, that would be probably a red flag that something is going around our support. But we are not able, in my opinion, to capture the really detailed interaction of the support with this type of approaches. We would need to have some sort of distinct element or particle flow to see how the body would move, like in a flow analysis, water around a pier or something like that.
I think it's important to realize everything that we're presenting here today, there is an inherent stickiness between the pile and the soil that we're not breaking, if you want to look at it in simple terms. So you have to, I mean, you can pull on the model and make it deform, but at some level, you're not able to actually have soil flow around a pile and nodes detach from the pile. So that's essentially, that gets into large strain, and like was mentioned by Augusto, other numerical methods where you're not attached to the pile.
I think this particular question is in the realm of the art of foundation engineering rather than the science. So I think we have to rely on a great deal of experience and observation of cases in the field. And as I'm sure you know, one of the long time observations is that if the pier spacing in general, if the pier spacing is not greater than 3 diameters center to center, which would be 2 diameters edge to edge, that there, to my knowledge, there have been no flow through problems observed for cases that met that maximum spacing criteria, those maximum spacing criteria. So that's a kind of a safety net place to start, I think. And as Augusto mentioned, it's our current analysis do not really address that directly. So in the meantime, I think we have to rely on experience and judgment on that.
Yeah, I think that 3D rule of thumb is a good one to keep in mind. Dr. Gregory, we'll stay with you. There were a couple questions about how you came up with the pressure distribution or the resultant force that you then distributed over that 9.5 feet. How did you select exactly where it was, and how did you come up with the magnitude of that force?
Again, it's mostly judgment and experience, but looking at a fairly large number of finite element analyses of those conditions and doing a detailed look at the stress distribution, it typically shows a concentration of stresses around the third point of that, what I call the free length from the slip surface up to the actual ground surface. And the percentage of that height over which most of the stresses were concentrated has been in that range in my experience and looking at finite element analysis and a limited number of instrumented cases. There's not too many of those, but all of that together has indicated to me that it's somewhere between 10 and 20% of the free height. And the deeper it is, the larger the percentage may need to be, but it's not real sensitive to that. You know, as long as the total magnitude of the force is applied, whether it's over 10% or 20% of the height, it makes some difference, but within the realm of the other parameters that we don't know very well, I think it's not real critical, but I certainly believe it's within that range of 10 to 20% of the tree height.
Yeah, okay, thanks. Yeah, right. I mean, just thinking in terms of the statics, it shouldn't change the shear force. It would only change the moment, because you're only changing the moment arm if you're not.
Yeah. And might point out, like in L-File and some of the other software is the same, it's very easy to vary that length and see how it affects things. It's just a few minutes really to do that, and that's typically what I do.
Yeah, very good. Okay, next question. Was the slope determined or assumed to be stable to the extent of not needing to consider active landslide forces on the piles? So I think if I read into that question a little bit, maybe the intent of it is something like this. The slope was computed to be almost stable with a factor of safety right around 1 for the current conditions. And I think that's relevant because a lot of slopes we address are like that, right? If the factor of safety was drastically below 1, it implies that the failure happened, and by the time we show up on the site to fix it, it's not moving anymore. So we're often dealing with slopes where the starting point is a factor of safety of, give or take, 1.0, meaning by definition in the limit equilibrium sense, it's stable, it's not moving. As soon as we put even just a little bit more resistance into it, we get our first drilled shaft installed or 1 anchor, we should be theoretically going over 1.0, and therefore it's not moving anymore. And so there's not going to be, or I guess this is the question, it's kind of philosophical, is there even more load that gets applied to the deep foundation or the structural elements? Or is it entirely fictitious and just plays into this idea of calculating a factor of safety? Anybody want to comment on that?
Well, I guess I took the lead in starting. Yeah, that is absolutely important to consider. What we are doing with the strength reduction analysis, for example, we are just imposing a stress path. We are triggering a sort of a stress reduction in order to develop some sort of displacement and see what type of interaction we are getting. It is fictitious. There is no other way around it. Either we are willing to really accommodate the physics if we understand it and we have enough data. That could be for water pressure variation, and Murray showed an example, for example, of a plain water table, which doesn't seem to be so significant. It was in the order of 5-7% of variation, and or mostly of the slope are creepy. So we should try to make an effort to add the fourth dimension in your question, Ben, that you were showing at the beginning, including time.
Mm-hmm. Sure.
I like to call that factor of safety when the slope is marginally stable to start with, and we increase that factor of safety as just a latent factor of safety. And obviously, if the loads imposed on the slope never change, then the reinforcement's just in there for the ride. It's not contributing. However, most places where there's been a problem, and it's a little different when we're designing from scratch and going to build right. Most of them, though, is when we're addressing a case where there's been previous movement or distress in the slope. And when it comes to marginal stability, that is probably the best case that it's ever going to be in without some modification to it. So the chances of loading due to rising water tables or other loads imposed on it, seismic, whatever, the chances of those happening are very high if the slope is sitting there with a factor of safety around 1 where it has come to equilibrium. And during the functional life of the facility, it's probably going to be called upon to have more resistance in the future.
Right, exactly. Okay, final question here, and then again, just a reminder, there have been more questions, so we'll try and get those answered in written format. But final question for discussion. To paraphrase, there are some differences noted between when the small strain theory or the kind of limit equilibrium approach is applicable versus the need to investigate in a robust manner larger deformations using finite element analysis. So the question I'll put to you maybe more broadly is, what's a rule of thumb for when it's necessary to go beyond a limit equilibrium analysis and go into a finite element or finite difference analysis? I think this is particularly relevant given the poll where 80% of our respondents said they're usually doing limit equilibrium analysis. So what are some flags that you might encounter that would make it necessary to do a more robust analysis? And likewise, a related question, there was a question that simply said, when do I need to do 3D analysis? So I think that kind of goes along with this. Anybody want to take that one?
Can I go first?
I'm gonna let somebody else start.
Okay, for the finite element analysis, this is what we recommend all the time. When we have any critical surface in limit equilibrium analysis, the best check is to do shear strength reduction. So if they match, it means that the limit equilibrium analysis is correct. If they don't, depends. Some cases like coupling, they don't match. But most of the times they have to match if you use advanced search methods in the limit equilibrium analysis. And regarding 3D, depends on the complexity of the geometry, complexity of the region. We showed in the results that you can go from 0.8 to 1.1 factor of safety. One section is failure, one section is not failure, but the overall 3D factor of safety is 1.2. So when your geometry is complex, you cannot trust just the 2D section. For example, when you have an open pit, you cannot just trust one 2D section on one side of the open pit. You have to do an overall 3D analysis. So depends on the complexity, you go from 2D to 3D.
Okay.
I would just highlight too that, I mean, basically, if you're going from LEM to FEM, LEM just strictly does not consider deformations. So if you're ever in a case where you need deformations, we get questions about that all the time, I would say, is how do I calculate deformations in LEM? The bottom line is it's not formulated for that at all. So don't go down that path. I think that's a clear indicator of where you want to go to FEM. It should be noted, however, that for base cases, there's been a fair amount of research done. If you have basic slopes and you're modeling them in LEM and FEM, the answer is going to be extremely similar. Like it should be within probably 2 to 3% as just a ballpark, because you're modeling roughly the same thing. The key indicator here, in my mind, that differentiates is you have a structure in the ground, and you have an interaction between the soil and the structure that is complex and that changes as the structure deforms. So you're modeling that stress path and you're seeing the impact of the structure pushing back on the movement, which right away you can't do that in LEM. So I would say that you have to put those mileposts in your head. Is there a complex structure? Is there a complex stress path that is being followed in my potential failure? Going 2D to 3D, I mean, there is probably 6 or 7 things that make a 3D analysis different. Like its topology. Is your topology different in 3D? Well, it is in this case, for example. Is your pattern of supports different? Yes, it is in this case, because the piles are spread in not a linear fashion, at least in the proposed design. What about my water table? Well, the water table was varying in 3 dimensions in this, according to the data. So that's another 3D effect. Then do you have a stress from a building or a ground? You know, like that's a 3-dimensional effect. So all of these things potentially introduce variance that is your professional judgment. Do you want to include it? I think it takes some professional judgment, but it's there and it's real. And I would say that, I mean, there's a bit of a balance. I mean, we want to model these things in FEM sometimes to model the very detailed things. You're looking at a pretty severe runtime increase once you get up to 3D and all the interactions, whereas it's a lot simpler to model it in LEM, and you can do it in a fraction of the time, I think is the interest for the practicing consultant. So there is a bit of a balance for how much can I reasonably invest in modeling for this and capture the main mechanisms and, you know, still provide value to my client and a reasonable design. So I think there's a professional judgment still needed, as well as improvements in computational time and software tools. So.
All right, very good. I think I'll add to that from what I saw in everyone's presentations, the reason you'd go to 3D is if you need a higher factor of safety to make your project work, basically. I say that somewhat sarcastic.
I would push back that you're going to a more realistic factor of safety that you don't know what it is, and you've been relying on it all these years because you know that 2D is conservative. You just don't know how conservative. So maybe to just push back, but that's a funny way to put it.
And also we had to keep the spacing of the support. We could change it to make it more reasonable, but we didn't go that far.
Yeah.
Two things to keep in mind. First of all, to go to a phased approach of more and more sophisticated analysis requires an extraordinary level of knowledge of the soil properties, which we usually do not have. Even on fairly large projects, there's a lack of data. So some of the methods that are more sophisticated can still accommodate parametric studies where you vary the parameters and that sort of thing. But it's only as good as what we put into the analysis on any level. And if it's a smaller slope with less overall cost or consequences or potential for cost savings involved, then we're probably looking at using lower level of analysis with a larger factor of safety that historically has proven to be okay. When we get into a much larger project or much larger consequences of failure, cost savings potential, those kind of things, then it would behoove us to go to the more sophisticated analysis and the 3D analysis. But I think as practitioners and the folks that are actually doing the projects, that has to be determined early enough in the process that the actual recovery of samples and laboratory testing of more complex properties can be built into the system. Because if you decide that at the end, as a practical matter, you're not going back and re-drill the site and retest and get those things. So it's a process all the way through for that sort of thing. One other point, 3D factor of safety is not equivalent to 2D if we're meeting some criteria. If we set a criteria for the project that, based on our experience and knowledge of 2D all these years, and we say the factor of safety target is 1.3, and we get a 1.15 with a limited equilibrium, and we run a 3D and we get a 1.3, that does not meet the criteria. Factor of safety of 3D is not equivalent for several reasons. One, our entire history of what a factor of safety means has been based on 2D up until recently. We don't have a database and an experience base for that. Secondly, most of the models use a elastic perfectly plastic model, a more Coulomb type model where we can't easily model a curved strength envelope, a non-linear envelope. And in a 3D, there's much more of the slip surface that is shallow. And that's where the error can come in a shallow, a low stress range, and where the curved envelope is more appropriate. So have to be careful if we're running 3D. It has a weakness in that unless the model itself can handle a true curved strength envelope. So.
Sure. Very good. Okay, I think I'm going to conclude it there. We've gone over, so I'm going to hand it over to Teresa Engler to make a few announcements for DFI and about upcoming events. But one final time, I'll note that we did have a bunch of questions that just came in the past 10 or 15 minutes, and so we'll do everything we can to get those answered in written format and sent out to all the attendees. So thanks again to the panelists, and Teresa, will hand it over to you.
All right. Thank you all. Yet another great discussion. This has been going on for a few years, and I'm glad to see that despite everything going on, we were able to continue it. I especially want to thank Roberto for hanging in there while we were trying to figure out what to do with the S3 conference. And also, thank you, Ben. Great job, both of you, and even your introductory videos to get people to sign up. I'm pleased to see that we had over 200 people at most of the time during this event today. So thanks for everyone who's hung out till the very end. I think that was the best part, to really hear everybody's opinion on everything. I also, going to get to the next slide. So all these people were instrumental in putting together the original program that we thought we were bringing to San Francisco. And I'm pleased to say they've all agreed to stay and help us bring it to you next August. And our hope is we will all be together in person, and that you will be able to hear the other great presentations that were planned. So keep your eyes out for that as we continue to plan between now and then. Of course, we always want to thank our sponsors. We've been very, very fortunate throughout all of this with all the changes we've had to make to have many of our corporate members continue to support our events and our activities. This time Berkel stepped up and took the main sponsorship, so thank you. And we also had 4 other sponsors, and if you look at the final program, you probably already did, they have an ad in there that explains their products and services. So we encourage you to look at that and go to their websites, and I'm sure you'll find something when you need it. And always thank you to all the industry associations that help us get the word out and bring more people and more points of view into our events: ADSC, PDCA, ISM, and Federal Highway, and then industry publication Pilot Buck. We really appreciate that. So you've probably heard this a few times if you've been on the whole time, but we will be providing the recordings to everyone who was on today, and you'll also get your certificates, which I know are important for your PE renewals. So all of that will be coming to you, as well as a PDF of the slides that you saw today on the online proceedings site. So you'll get that within the next couple of weeks. So also, if you haven't received it yet, in the next few minutes or within the half hour, you'll be getting an email with a survey. And we do ask that you provide your feedback. It's always important for us to know what went well, what didn't, whether it's regarding the platform, the presentations, the information we're providing, and any insight you can give us into what you'd like to hear in the future. So as you see, Roberto will once again be our chairman for the conference next year. And like I said, if you put those dates in your calendar, August 3 to 5, we will be in San Francisco. So we're really hoping to see everyone at that time. A couple other events that we do have coming up that I just want to make you aware of is our Super Pile Conference, which was this year also an online event, and we're hoping next year it will be in Philadelphia. You can see our chair and program chair here, Jared and Justina. And there's still time if you want to be a presenter at that event to send in an abstract with your presentation proposal. And that's due by October 30th. So if you go on our website to upcoming events or dfi.org/superpile2021, you'll see all the details on what topics they're looking for. And last, but definitely not least, we will not, unfortunately, be in National Harbor in mid-October this year. But once again, these chairs, Sebastian, Jennifer, and Greg, are excited about this new opportunity to present an online conference. We are putting it together on a new dynamic interactive platform, very different than this, that's going to give you a lot more opportunity to actually see each other. It's tough when you can't see all the 200 people that were listening, but here you'll be able to go into networking lounges and exhibit booth video chat rooms and get a little bit of that networking that we're all missing, and time to see how everyone's doing and see what their needs are from a exchange of information standpoint. So we have changed the dates. So if you didn't see the announcement that came out recently or read the magazine article, the new dates for the annual conference are October 27th to 30th. So it's a couple weeks later than originally planned. This will give us and our exhibitors and our speakers a little bit more time to learn the platform and bring you the best experience that we can. So thanks once again to everyone who was on the call today, everyone who's presented, and hoping to see you soon. Thanks. Have a great day.